So hello everyone and welcome to my course. So the first question is, who should take this course? And the best answer is, this course is made for security engineers, hackers, pentesters, reverse engineers, malware analysts and computer science students. These are the audience which can take this course, and anyone who has a hobby of learning of computers, uh, they can take the course. So after this question, we need to answer the second most important question, which is, what skills do you need in order to follow with me in this course? Yeah, or follow along with me with this course. Sorry for my grammatical mistakes. So what skills do we need? These are the skills which we need in order to follow this course. First skill is, you have some basic understanding of C and C++ programming, and you know the operating system internals, like basic operating system internals. You have a basic idea. After that, you should uh, have a basic familiarity with Linux shell, how to operate in Linux shells, and lastly, you should know a basic working knowledge of assembly syntax of x64 64-bit assembly. So these are the four skills which you will need in order to follow along with me in this course. So I will meet you in the next part. Till then, goodbye. Hello everyone and welcome to my course. In this part, I'm going to show you what kind of machine I'm using in my labs. This is the machine which I'm going to use in my whole series. This is Ubuntu 22.04.1 LTS, and with 64-bit of CPU, with the kernel version is this. So you can follow along with me with the same configuration installed in your virtual box or as your core operating system, as your main operating system. You can follow me with the same configuration. So I will meet you in the next part. Till then, goodbye. Hello everyone and welcome to the next part of binary analysis. In this part, we will try to understand what is a binary. So as you can see on my screen, we have two files here. One is hello and another file is sample.txt. So let's see what is the difference between these two files, right? So let's try to see the permissions of these two files. As you can see, this green colored file hello has some read, write and execute permissions, while the other sample.txt has only read, write permissions. So this indicates, this is the first characteristics of a binary file, which is it can execute. It has the ability to execute. Now if we try to execute this text file, it doesn't execute. It will not execute. But if you try to execute this hello, it will going to execute. This is hello word output. Let's try to execute this, because this doesn't have any execute permissions. If we try to give an execute permission to this file, sample.txt, let's try to run sample.txt. Now what it is giving result? Command not found. Now it is trying to execute the commands or trying to execute the instructions which should be written in this text file, but this text file has simple text in it. This is the content of this text file. So the first difference is it has execute permission. The binary file contains or has execute permissions, while other files which is not executable files doesn't have execute permission in them, which shows that this binary file has or this binary file contains machine instructions to execute. So if we want to define what is a binary file, we can say that a binary file is a file which contains machine code, and we can see that this hello binary file has machine code in it. We can see that, or we can clarify this by the file command file hello. As you can see, the output of this file command is this is an ELF file which is 64-bit executable. Now if we want to see the contents of hello, we can see we can analyze with that, or we can see that the contents of hello with the object dump command by disassembling it. Object dump -d means disassembling, and then hello, and I am just using less. So these are the contents of hello binary file. As you can see, these are the machine instructions, these are the machine code, and these like when this binary executes by the system, these instructions will get executed. So this is like, these are the machine codes which executes when this hello binary executes. So now we get the idea what is a binary what is a binary file. Binary file is a file which contains machine code and which can execute in the system. I hope you got my point. I will meet you in the next part. Till then, goodbye. Okay, so welcome to the another part of binary analysis tutorial. So in this part we will try to understand, or we will try to explain, I will try to explain you what is the life cycle of a compilation of binary, or binary compilation life cycle. So when we compile any source file, in this example we have file.c. This is a C source file. If we compile this source file, we get the binary executable. But before getting binary, we have to understand what are the phases of compilation, what are the phases of compilation process in which it has gone through start to finish. We have to understand all these processes. So let me give you an outline. I will give you an outline, theoretical outline, and after that I will show you all these steps practically one by one. So the first phase is pre-processing phase. When we give the compiler to compile any source file, what it will do the pre-processing phase of that sample file, or of that source file. So after the pre-processing phase, it goes to compilation phase, in which the compiler will just assemble the file in assembly code, and then this assembly code will gets converted into object file. Then this object file will again converted into binary executable by the linker. So this whole process seems to be little bit like confusion, but once I will show you some practicals, then it's very easy to understand. So let's go for the practicals. So this is my screen, as you can see. Now we have like hello and sample.txt. Let's remove these two files first, and let's try to create a simple C source file like hello.c, and let's try to write some some simple codes in it. stdio.h, standard input output file, header file. Then hash define message, then hello world, then int main, then printf. In printf we have the message, and after that we just return. This is a simple program in which I am using hash define preprocessor directive, which defines message hello world, and I am using this message to printf. Just for the demonstration purpose, I will like you will understand why I am using this message here. So let's try to compile this first. gcc space and hello.c, and then enter. We have the a.out. We can execute this by a.out. This is hello world. Now let's remove a.out. Now let's start the stage 1. Let's try to go to the stage 1, like phase 1. In the phase 1 is pre-processing stage. Let's try to see what a compiler does with pre-processing stage. So for getting for showing you the pre-processing stage, we have to use two options. First is -e option and second is -p option. I'm using these options of GCC because I have to show you the pre-processed data of this source file. So I'm telling GCC that please stop the compilation process after the pre-processing stage finished. So let's try to give this file, and let's dump the output into a new file called preprocessed hello.c. And now we have another file which is a pre-processed data of this hello.c file, c source file. Let's try to see what this pre-processed data has, what this pre-processed file contains. Let's try to less pre-processed source file. As you can see, these are the some type defs. These are the type defs, some structures, whole bunch of structures, and in the last few lines you can see our main function. And in this main function you can see clearly that this printf has clear hello world message. I have used msg tag, hash define preprocessor directives tag msg. Here that msg doesn't shows up because in pre-processing stage all the hash include library files gets expanded. We have used the hash include stdio.h std, whatever we have used here in like whatever we have included with the hash include, it will get expanded in the pre-processing stage, and whatever we define here as a preprocessor directive, these will be expanded wherever you have declared these definitions. It will be expanded in the pre-processing stage. So now you know what is a pre-processing stage. In the pre-processing stage, all the hash define and hash include library files will get expanded. So this is the pre-processing stage in which all the definitions or all the library files which is included on the top of your program gets expanded for the compilation. And the expanded file looks like this. As you can, this is the expanded file. This is expanded source file. This looks like this big file. Now this is the first phase. This is the pre-processed source file. And now what we can do, we can move on to the next process. As you can see on the diagram, we have clearly done this phase. We have clearly done this pre-processing stage. So we have clearly passed pre-processing stage, and now we are going into the compilation phase. So this I will cover it in the next part. Till then, goodbye. Hello everyone, and welcome to the binary analysis course. In this part, we will try to assemble our source file. In the previous part, as you can see on my screen, we did the pre-processing stage. We have completed the pre-processing stage. Now we are going to compiler and ask the compiler that just take the pre-processed input file and convert it into the assembly file. This is our next stage. So let's do this. Now we have our pre-processed source file, and now what we can do, we can we can use GCC, and for the assembly, in order to perform the assembly, or use the assembler to assemble the source file into an assembly file, we have to use -s, capital S option, and we have to give the input as our source file, as source input file. So we have our preprocessed hello.c, and we have to hit enter. Now we have the assembly file. Now we have generated assembly file. GCC has generated the assembly syntax, or the GCC has assembled the preprocessed source code into the assembly file, into the assembly. As you can call it dump, or whatever you can call it file. So this is the assembled data. Now we can see that assembled data like this in nano preprocessed hello.s. As you can see, this is the assembly language. Now here you can see we have our string hello word, and it has a label called .lc0, and this is our main function. In the main function, this is the whole main function code in assembly. If you notice, this hello word is used somewhere in main function. If you know like basics of assembly language, basics of assembly syntax, then you can find this string in the main function. So if you see, if you watch carefully, you can see this .lc0 is used here, because this is AT&T syntax of assembly. So this LC0 is transferred into RAX. I mean, this .lc0 address is transferred into the RAX, and this RAX address is moved into RDI register, which is the address of hello world. And after that there is a call to puts, I mean printf function, which just prints the hello word, and then it will exit normally. So this is the system call in assembly. This is the print system call in assembly, or you can say write system call. So this is just an assembly. It has prepared the code for the assembly, like it has created the assembly which needs to be converted into the machine code. This whole assembly will be converted into the machine code in the next step, when we create object files from this source file. But I mean, this we will create the object file, or you can say machine code, from this assembled code, which is actually an assembly language code. And there is a bunch of other codes you can examine in your free time, but my whole purpose is to educate you with few things which you can trace out here, which is a system call to print the hello world string. Now let's exit this, and I will see you in the next part, when I will show you in the next part I will show you how to convert this assembled file into object file, or you can say machine code. I will meet you in the next part. Till then, goodbye. So hello everyone, and welcome to the next part of binary analysis. So in this part we are going to create our object file. In other words, we are going to take our assembled file, and create a machine code from this file. So in order to do this, we have to use -c option of GCC compiler, and we have to give the assembled file, which is, in this case, we have preprocessed hello.s file. So let's give it and then hit enter. Now we have an output called preprocessed underscore hello.o. .o means this is an object file, and object files are nothing but machine codes. So we have converted this assembled file into machine code. And if you see the flow chart, we have completed this stage. We have assembled, then we have created our object file, which is nothing but machine code, machine instructions of our source file. So we did 3 stages: the pre-processing stage, assembly stage, then object file creation. So for now we have the machine instructions which is stored in this file, which is an object file, and we can further give the compiler our object file. We can give this object file to our compiler and ask that take this object file and convert it into binary executable. Then this compiler will take this object file and give it to the linker, and the linker will do? Linker will link all the library addresses into this object file and create a binary executable. So this let's do this. For now, let's create the binary executable. Let's create the final binary executable. Let's use GCC, our compiler, and give the object file as an input, and in output we can mention the output. In this case we are going to use hello as an output. So now we have successfully compiled our hello binary. You can see if we run this binary, we get the output. So we have completed all these stages. Now we have completed all these stages. In the next part, I will tell you what is the difference between object file and a binary file, and what is the linker in between these two phases. What is the purpose of linker in these two phases, which is a very important concept in compilation. In the next part, we will focus heavily on linker phase, like linking phase, when a linker takes the object file and convert it into the binary file, what it does in this stage. We will try to clear the concepts. So we will meet in the next part. Till then, goodbye. Hello everyone and welcome to the next part of binary analysis. So in the last video we have completed the overall process of the compilation. We have successfully created our binary executable. In this video we will try to understand what is the purpose of linker and what is the difference between this object file and this final executable binary file. So let's try to understand the linker role in this situation. So what a linker does in this case, linker takes this object file and put some addresses of the library files, right, and these addresses will copied into this object file, and then it will be generated as an executable file. I mean to say, this object file doesn't have any addresses. This object file doesn't have any proper addresses, which is a result that we cannot execute object file in the system. If we try to execute an object file, let's if you see, this object file doesn't have execute permissions, which shows that it can't be executed. Why it can't be executed? Because this object file doesn't have any mapped addresses. Like if you want to run a file in the system, it needs to be mapped to certain library functions, certain library files and functions. So it is necessary it is necessary part for the linker to put some addresses of library files into this object file and then convert it into final binary executable. So the purpose of linker is to just link all the addresses of library files and create the binary executable. Means it wraps all the addresses of library files into this object file and then generates the final output, which we call binary executable. And when we execute this binary, we will get the normal output. So now the question is, why we can't execute this object file? Because if we compare both the binary and object file, the final binary output, this executable binary and this object file, the changes are very minor. Let me show you the difference between object file and binary file. Now we have this window, second terminal. Let's try to differentiate the object file and our binary file. First, let's try to load the RO data section. Read elf -x and .ro data section of preprocessed data.object file. Now I have used -x for the hexadecimal format, the dump of RO data section in the hexadecimal format. Now we have dumped the .ro data section. This .ro data section is nothing but read-only data section of this object file. As you can see, this is the memory address of this string, and this is the hexadecimal value of this hello world. And now watch carefully here. We are dumping the .ro data section of the binary hello, and in this situation you can see this memory address, this is the memory address which is something like it is 2000, and here it is 00. So this is the difference between this executable file and this is object file. I already told you that object file doesn't have the addresses, doesn't have the linked addresses. That is why it is showing that this is a 0, the address is 0, and this final like binary executable file has the address. This is the address, assigned address. Now this is the first difference. I told you there are many differences. Now let's take another part, which is like object dump of not sj but let's try to disassemble our preprocessed data.o object file. As you can see, I have dumped this object file data with object dump, and here you can find this is the main function disassembled code, and you can see this main function has 0 address. This main function has a address of 0, which doesn't make any sense. And if we use the same command, object dump, and disassemble our hello file, hello executable file, we can see that this hello file has many instructions, at least like it has more than like this object file has only few lines of assembly instructions, but in the in this case in our binary, fully functional binary, we have all the different types of sections in it. So we have to focus in our main section. Let's focus in the main section, and this is our main function instructions. So as you can see, this main function has a proper address This main function has a proper memory address, while it doesn't have any kind of address. If you watch carefully, you can see here when it loads the address of our string, which is hello world in this case, this is transferring the address of hello world into RAX, and then this RAX is copied into RDI for the printing purpose, for the printing. And in the next step, there is a call to the puts function, which just prints the just prints the hello world string. And in this case, as you can see here, this shows that this address is 0. The 0 address is transferred into RAX, and this RAX into RDI. Then again there is a call, but this call doesn't have a proper function call. This is calling line number 17, which is here. In line 17 there is an exit function, so there is no printf function here. So this is just plain, as you can see, the instructions without addresses, without memory addresses. These are the instructions. Instructions are correct, but this doesn't have any proper address. And in our final binary, we have proper addressing. So this addresses, so where are these addresses came from? These addresses came from the linking. These addresses are came from the linker. The linker has put all these addresses into the object file and created a new binary executable file. So I think you got my point. What linker does with the object file, it just takes the object file and copy all the memory addresses of the library files into this object file to specific locations in this object file, and then creates the binary executable file. So this way this linker works in this kind of phases of compilation process. So I will meet in the next part. Till then, goodbye. So hello everyone, and welcome to the binary analysis tutorial course. So in this video, let's try to understand the ELF file format. Actually, we are going to understand the structure of ELF file format. So let's see. First question is, what does ELF contains? So as you know, every file contains binary data, which is in the form of 0 and 1, which is further converted into hexadecimal form. So we can say that ELF file is a collection of hexadecimal bytes. So ELF file is a collection of hexadecimal bytes, like this. You can see this is all hexadecimal bytes. This 7F45, this 7F is a single byte, which is hexadecimal byte. So there are hundreds or thousands of hexadecimal bytes, which is just a collection in the ELF file. So ELF file is a collection of hexadecimal bytes. So this is the first task in which we have defined a simple definition that what does ELF contain. So ELF contains collection of hexadecimal bytes. So this file contains hexadecimal bytes. Now the next, let's try to understand the next part, which is format, ELF format. So these hexadecimal collection is like these bytes. You can see this is a collection of hexadecimal bytes, which further is divided into some kind of categories. These bytes are divided into some kind of categories, and these categories are written here like executable header, program headers, sections, and section headers. So basically these hex bytes are divided into 4 categories, and these are the 4 categories which has the names. Like the first one is executable header, second one is program headers, third one is sections, and then fourth one is section headers. So basically these bytes are divided, or you can say grouped, into 4 parts, and these 4 parts have a name. And what are the names? These are the executable header, program header, sections, and section headers. Now let's move on in order to understand the structure or format of the ELF. So this is the structure which we have seen, that it has 4 categories, or you can say 4 groups, in which these hexadecimal bytes are divided. Now let's see the first category, the first group, what this first group contains, what kind of information this contains. So the first one is executable header. So this executable header is just a structured series of bytes. We already know that these are the bytes. So what these bytes tells us, these bytes tell us that it's an ELF file. And what kind of ELF file it is? It tells that this is an ELF file, but what kind of ELF file is? It also tells what kind of ELF file is this, and where in the file to find all the other name, all the other contents, or you can say all the other group. So this particular executable header gives all the information about other contents also, like other parts of the binary file. Like this executable header has all the information of program headers, all the information of sections, all the information of section headers. So it holds all the information of the remaining sections. That is why it is written here, and where in the file to find all the other contents. If we have to find program headers, we can go into executable header data. We can check out the executable header data in order to find out program headers. If we want to find out, if we have to find out sections data, then we have to go to executable header first and read it, the information, like it gives the information of sections. Then we can go to the section part, then we can read the data. And here is the same case also. If we want to get the information of section headers, we have to open the executable header information. So this is the first area of ELF which tells us what kind of ELF file is this, and it tells us also that where we can find the other contents or other groups in the ELF, like what are the addresses of these particular components, you can say components, what is the size of these components, where they are located, what are the counts of their contents. So let's move forward. So this is actually the information of this particular content, executable header. So this is the executable header information. As you can see here, this has like some magic numbers, or you can say magic hexadecimal bytes, and then class, then data, version, and then all the like different information. So I will cover all these information in the coming part. Let's move on to the next slide. So let's try to understand executable header first. Let's try to understand this executable header first. So I will cover it in the next video. So I don't want that video will be lengthy. So I don't want to be lengthy. I don't want to create lengthy videos. I will cover this section, this executable header part, in the next video. Till then, goodbye. Hello everyone, and welcome to the next part of binary analysis. So we have left here. So in this part I will explain you all the data or all the information about executable header. So as you can see, this I have used read elf -h option, like I have used read elf tool to see the executable header data, So let's go into the terminal and try to understand all the information of executable header. So let's go here. So let's try to create a file, and I already have a file which is hello.c. as you can see, this is simple code in C, which prints hello world on the screen. So we have this hello binary file for our practicals. So if we try to see the information, if we try to get the information from the file, we are getting ELF 64-bit executable file. So this is ELF 64-bit file, which is executable file. Now, in order to see the four groups which I have already told you here, like this. This has four groups. ELF file have four groups. You can say contents, or you can say components. So ELF file has four components: executable header, program header, section, and section headers. If we want to view any of the components, any one of the components, we can view by the help of a read ELF tool. We will use read ELF tool. read ELF tool to view the contents of those particular component. So in this case we are interested in executable header component. So if we see the help options, so like if we see the options of read ELF executable, we can see that if we want to view the program header, if we want to view the executable header component, we have to provide -h option which displays the ELF file header. So let's try to use it, ELF-h, then our file which is hello. So as you can see here, this is the same information which I have already shown you in the slides. So let's try to understand one by one these parts. So let me first let's dump the hex values side by side. So hex dump -c and then hello. This is the file, and let's grab it first. Let's grab it first 3 lines, and we are filtering out ELF. So this is the first 4 lines of hexadecimal dump of this particular hello binary. Okay, so I will come this part later, but let me first explain these information to you. So let's start by going to ELF header, this particular label. So this is simply a label where it shows that these are the information of ELF header. So the first information is magic. This magic, what this magic is. So this magic contains these hexadecimal values. You can see if you count these values, these are 16 bytes hexadecimal values starting from from here. So the first 4 bytes are magic bytes. These first 4 bytes are called magic bytes. That's why the label of this particular section is magic, which shows that this is a magic byte. The first 4 bytes are magic bytes. Now the first byte, which is in hex form, which is hexadecimal value, this first hexadecimal byte is a magic value which defines which type of file is this, which defines which type of file is this. Likewise, the next 3 bytes defines this ELF characters. This E denotes this 45, then this L denotes 4C, and this F denotes 46. So this 7F is just a magic byte to detect which kind of file is this. This is a special byte. It changes or it is already defined in the system for different kinds of file. So for binary this is 7F. If you see if you have like if you can try to view a JPG file, or you can say any image file, or any audio file, any video file, any kind of file. This value changes in every in every type of file. It doesn't like uh, it's not necessary that binary the file is should be binary. It can be any kind of file, but this first byte shows the type of file. This first byte, this is 7F. If you open an image file, that image file has different byte, different byte here. So this second, third and fourth byte is nothing but ELF. This ELF ASCII characters. These are the ASCII representation of hexabyte, sorry, hex byte, ASCII representation of ELF, which is 454C and 46. So these are the first 4 magic bytes. That's why it is called magic bytes, because it defines the type of file. The next byte is 02. This 02 is nothing but this information, which is class. This 02 this 02 indicates the class. This 01 indicates data, this data. So this is actually a translation, like this is translated into an information, you can say mapped mapped into some kind of information in the binary. So this 2 shows that this is an ELF 64 byte, so sorry, ELF 64 bit version file. This hello is 64-bit binary file. This 2, this 02, this hexadecimal byte shows the class information. The next 01 byte shows the data information, which is the little endian data. This is a little endian data which has a 01 hexadecimal byte. 01 defines that it is little endian data. If there is 02, if here there is 02, then it will be big endian data. So if the value here changes to something else, these data also changes accordingly. Then we have again 01, next 01, which is version. This version part, this version is 1, as you can see, this is 1. Now the next one is OS ABI. This OS ABI is operating system application binary interface, which tells the operating system that this particular binary is made to run on this particular operating system. Now this is a special category of operating system. This is Unix system 5th kind of operating system. So this binary can run on only on these type of operating system. So this is OS ABI, which tells that this is the type of operating system on which this binary is compiled to run on. So this is the part of this particular information is this 0. So this 0 byte shows this particular information. Now the next information is next byte is 0, which is ABI version, which is nothing but just ABI version, this ABI, application binary interface. This is 0. So as you can see, this is 0. Now the remaining part, the remaining bytes is reserved. The remaining bytes are reserved for future use. So all these bytes are used till here, till these, like all the bytes till here, 1 2 3 4 and 5. So 1 2 3 4 5. So till here all the mappings are till here. Okay, so these are the information which is hidden inside these bytes. If you watch carefully in this hex dump, let me show you this secret. You can see this first 7F454C. Now this binary is starting from this byte, this first byte 7F. The first byte is magic byte, which is 7F, which defines that this is an ELF file, means this is a binary file. So you can see here, this is 7F, this is 7F. Now you can follow the next byte, which is 45. You can see this 45 bytes. If you look carefully, these 16 bytes, are here, and all these data is mapped accordingly. All these data till here is mapped accordingly in these 16 bytes. So these are the first 16 bytes which holds the information till here in the ELF binary. So after the 16th byte, after the first line, we have the next information, which is type. This type shows which type of file is this. Is it a library file, is it a binary file, or it is something else? It is an object file. What kind of file is this? So this is the type, and this type is right now it is showing DIN, or position independent executable file. So this is an executable file. It is showing that this is an executable file, and which byte holds the information of this particular column, this type column. So the byte is this 2 byte. This 2 byte holds the information of type. So this is, as you can see here, this is 03. So these 2 bytes are reserved for holding the information of type in the ELF file, in the ELF header file. If you change the value, if you change this value 03 to 02 or 01, this information will be changed accordingly. And now the next part is these 2 bytes is for type. The next byte, next information is machine. So this machine information shows that this is advanced micro devices. This particular information shows that this particular binary is made up of, like this particular binary runs on these types of machines, and the uh, code, the hex code, is mapped to these 2 bytes. The hex code for this information is uh, stored here in these 2 bytes. So this information, machine information, is stored here in these 2 bytes. The information is 3e 3e in hex. If you change this information to something else, then it will change accordingly. So these are the 2 bytes which holds the information of machine. Now the next part is version. So the version is 1, and these 4 bytes, the next 4 bytes holds the information of version. And then after, we have entry point address. So the entry point address, this is an entry point address. This is an entry point address. So you should have a clear understanding of what is an entry point actually. uh, Entry point is the program's entry point. I mean to say, if you look at our source code in the C file, in the C, so like hello.c, this is our main function. This main function is the entry point of our program. Whenever program tries to execute, it will execute from here. So this is the entry point, and the address of this entry point is this. So this is the entry point address. This is the address from where the program starts its execution. So this information is stored in these 8 bytes. So this information is stored in these 8 bytes, which is 6. You can see this 60, this 60, and this 10, this 10. So these 8 bytes are reserved for the entry point addresses of the program. Now the next part is start of program headers. So this start of program headers is 64, which shows, if you convert this 64 into hexadecimal, let me convert it in hexadecimal format. X, new line, and this 64, you can see this is 40 in hexadecimal. So the start of program headers, the address of the start address of program headers is this. This is the 8 byte which holds the information of this line, this particular start of program headers line. So this is 64, which is 40 in hexadecimal value, as I can converted it here, 64. So this is 40, as you can see, this is 40. So this information is stored in here, which is like these 8 bytes are reserved for this particular area, start of program header, which is 64. Now the next part is start of section headers. I will show you what you already know what is section and what is section headers. I already given you a brief introduction of four groups of the ELF file. Let me show you again. So you can see section headers, sections. So this is the same part. We are here, start of program header 64, start of section headers, and then all the other parts. So I am just mapping all the information. I am mapping all these information into the hex dump, hexadecimal dump of the ELF file, so that you have a proper mind map. So in this way you have a mind map, so that you can relate these information. You can relate these information into the hexadecimal dump of the binary. So this was the program headers part, and the next one is section headers, start of section headers, which is 13968. So if you look carefully, this 8 bytes shows this particular information in hexadecimal. Like these 8 byte holds this particular area of information. If you convert 13968, let me convert you 13968, it would be 3690. So it is 3690. So this 8 byte area holds this particular information in the ELF header. And then we have flags, which is 0 in this case. So this flag holds these 4 bytes area. This flag information holds these 4 bytes area. The next one is size of this header, which is 64 bytes. So these 2 bytes hold this area, this size of this header. The next 2 bytes holds the program headers, which is of 56 bytes, size of program headers. I will cover these parts in the coming videos, don't worry. I'm just the task here is to map the ELF header to its corresponding hexadecimal dump, so that you can correlate the relations between these information and these hex bytes. So this 2 bytes is for this particular program headers. Now the next part is 13 number of program headers, which is 13, and this 2 byte shows this particular area. Now the next part is size of section headers, which is 64 bytes, and if you convert the 64 into hexadecimal value, you can you will get 40. So this 2 byte shows this particular area, and this particular area holds these 2 bytes. Like this information holds, not this. This particular area holds this information, these 2 bytes. Now the last 2 bytes holds this area, section header string table index, which is 30. If you convert 30 into hex, you will get 1E, which is 1E. So these 2 bytes are reserved for these information, this last information. So you can see these hexadecimal digits have some meaning. These hexadecimal digits have some meaning. That's why I have mapped these information to these. The reason is you should have a clear mindset. Whenever you are going to analyze any file, you have a clear mindset that what kind of information is this is giving, and how can I find and correlate these information in the hexadecimal values in the dump, hexadecimal dump. Okay, so I will meet you in the next part, and I will cover these parts. I will cover these parts, which is most important parts, as what is the start of program headers, then start of section headers, then size of this header and size of program headers. I will cover these parts in the next video. Till then, goodbye. Hello everyone, and welcome to the next part of ELF binary analysis. So I already covered these things. Now we are moving forward, we are moving to the next part, in which I am going to show you the meaning of these information. What is the meaning of these things, these informations from the executable header info. So as I already told you in the previous slides, that this executable header contains the information of other parts, information of other groups, you can say. This executable header information holds the information of other groups also, and these are the other groups, which is program headers, sections, and section headers. So let's see what information it holds in the executable header. So if you look carefully in the output of executable header information, which I have shown you in the last video. So this is the same output, in which you can see here number of program headers. So this is the information, number of program headers, which is 13. Now this 13 indicates that this program headers are of number 13, means this ELF has 13 program headers. Okay, so number of program headers is 13, means this program header has a number of 13, like these program headers are divided into 13 parts, so these are 13. Likewise, if we see here number of section headers, which is 31, it is giving the information about section headers, and it is telling us that number of section headers is this is the program headers and this is the section headers. Okay, so now let me show you. I have misplaced my slides, sorry for that. Let me move here so that we can understand well about section headers. So these information are the same. So you can see in the previous slide we have seen that a number of section headers, number of section headers is 31. So these section headers contains 31 in number, so there are 31 section headers. It is showing that section headers have 31 parts. Okay, As you can see here, these are the third sh means section headers, and these are like I have represented these as a one part, one entity. So if you count these, it will end up in 31. So section headers are in the count of section headers are 31, which is clearly written in the output of executable header. Now the next information is start of section headers. It is telling us, or it is showing the information of the address where the section headers is starting. Now the first the first section header starts at this address. The first section header, the you can say the address of first section header is this 14056. So if you convert this into hexadecimal value, the address would be the address will indicate here. So these are the two information is the first one is number of section headers and the address of section header where it is starting, and the next valuable information is size of section headers. You can see here size of section header is 64 byte. Now this part is like very confusing, but let me clear you. Size of section headers is 64, means the every section header has a size of 64 bytes. You can't say that the size of this whole area is 64 bytes. No, the size of every section header part is 64 bytes. So there are 31 section headers. So each section headers has a size of 64 bytes. It means size of every section header is 64 bytes, and there are 31 section headers. Likewise, if you see carefully here in program headers, it is saying that start of program headers, means the address of program header will be this particular location, which is, if you convert this into hex, it will be 40. So the starting address of program headers is here. So here the concept will be the same like in section headers. How? Because program headers, the counting of program headers is 13. As you can see here, number of program headers is 13. So there are 13 program headers, and the first and the location of the first header, the address of first header will be here, and the address will be this 64, which is in decimal. If you convert this into hexadecimal, it will be 40. So this is the location of the first program header. This first program header location will be here. Now the size of each program header, the size of it is showing that size of program headers, which is 56 bytes. Now you will get confused here. I think it should it should be written like this: the size of every program header, size of every program header will be 56 byte. So each program header has a size of 56 bytes. So now the next important part is size of this header. I think I have covered everything. The last one is like the most important one is size of this header. Size of this header. Now the size of this header means the size of this executable header. Size of this executable header is 64 bytes. I already shown you, I already explained to you. Let me show you the 64 byte. This is the size. The first 64 byte is ELF header. As you can see, size of this header is 64 bytes. So this is the 64 bytes. The first line is 16 bytes. If you count 16 into 4, it will be 64 bytes. So the first 64 bytes is ELF header. How we are sure about this? Because the ELF header information shows this, that size of this header, this particular here, is 64 bytes. That is why it is 64 bytes. And I have confirmed you by looking all the information and tracing out every byte in this area till here. So these are all 64 bytes of information. So I think mostly I have covered most information here. I have explained to you. Entry point I have explained. Start of program headers, start of section headers, flags, size of this header, size of program headers, number of program headers, size of section headers, number of. I have covered everything except the last one, section header string table index. So this is actually let me open the slide and I will show you here there. Section header string table index is 30. So this is nothing but let me show you. Section header string table index is 30. This information is telling us that the count of sections, I mean to say count of section header, the count of section headers. So the count of section header is 31. As you can see, number of section header is 31. So this 31 is total count in decimal. It doesn't have an index from 0. But in section header string table index, because this is index, so index is always start from 0 in programming. So this start from 0 counting and it will be of 30. If you count from 0, it will be 30. If you count 31 from 0, it would be 30. So this is nothing but this is the index of section headers. So if you count from 0, 0, 1, 2, 3, 4, 5, then you will end up in the count 30. You will end up with 30. So this is the same actually. Number of section headers is 31 and section header string table index is 30. So one is starting counting from 0 and another is starting from the 1. So these two indicates the same component or the same information, which is section header. So these are the countings, which is if you index it you will get 30. If you don't index it you will get 31. So all these I have like explained all these information about executable header part. So I will meet you in the next part with other area with explaining other areas also. So till then, goodbye. Hello guys and welcome to the next part of binary analysis. So guys, in this part I will try to try to show you the difference between section headers and sections. This is just just an introductory video for section header and sections. So as you can see on my screen, I already told you that we have four parts of our ELF binary, which is executable header, which I already have covered it everything. And after that we have program headers, we have sections, and we have section headers. So before going into program headers, before understanding program headers, we need to understand section header and sections first. So in order to understand section headers and sections, we first go for section headers. So as you can see on my on the right side, I have pulled out section headers of our file hello binary file. So these I have used read ELF tool as usual, and I have provided -s capital S option, and then we have our ELF file. So the output shows the section headers. So these are section headers, and mostly guys, like most students confused, like they confused between section headers and sections. They think that section headers are sections, and they are not able to differentiate, or they are their conceptual their concept is not clear between these two in most of the cases. So it's important for me to clear the concept between section headers and sections. So this is the section header, this is the section header, this is a kind of indexed this is the indexing of sections. I mean, when we index something, index any data, it's called indexed data. So the sections are indexed, the sections are indexed in the section header. So as you can notice, these are the sections here, these are the sections, and these are the list of the sections. So these sections have indexing in section header, so that we can, or the program can find a particular section by going through these indexes, and these indexes are their addresses, where they are located in memory, their size, and their flag, means if they are executable, they are linkable, or they are readable, anything. So they program should program should have any kind, program should have indexing criteria, so that whenever program needs any kind of section, and any kind of section access, so program can go through these addresses and put the size, and put the permission, and then it program can use this section. So this is section headers are indexed form of sections. It's not actually a section. The data of these sections is not in the section header. Data is not the actual data of section is not in the section header. Data is in sections, data is in this particular category, data is in this area, the section data is in this area. But in section headers, these are only the indexed data. Indexed data means which the sections addresses on which these how can we find these a particular section, so that it has given the it has indexed the all the sections in a table so that we can find each and every section in the memory in this area, in this section area. So I hope you got my point. In the next video, this is just an overview of the section headers and sections. uh, in the next part I will clear the concept between the indexed data, or you can the section header and sections. So I will meet in the next part. Till then, goodbye. So hello everyone and welcome to the next part of binary analysis tutorial. So in this part, let's try to understand what is a section and what is a section header. So let's start. So let's first define the section. What is a section? So the definition, the common definition is the code and data in an ELF binary. The code and data in an ELF binary are logically divided into contiguous non-overlapping chunks called sections. So in one line we can say that the chunks of code and data in an ELF file are called sections. So basically section is a code, it can be a code and a data which are in chunks. So this is a clear definition, and this is an ELF showing, like I have shown you, this is a ELF file which is in hexadecimal bytes. So this is a group which is a code, and there is a group called data. So there can be a group of or chunks of data, chunks of code and chunks of data. These chunks are called section. So I think this is a very clear concept of a section. So section is nothing but chunks of code and data in an ELF file. So let's move on to the next slide. Now this is representation of a section, which is clearly I have shown you, this is the code and data, the chunk of code and chunk of data called section. Let's move on to the next slide and try to understand it more clearly in a real situation. As we already know, section is a chunk of code and data. So let's see what a section actually looks like. This is the list of sections. This is a init section, this is .plt section, there are many types of sections. So I have shown you few of these. So these are the examples of sections. So 1 2 3 4 5 6 7, these are 7 sections. So in these 7 sections, let me show you which, I will show you only 2 of these which has a code and a data. Now the first one is init. This is a section which is a code. This init is a section which is a code, chunks of code, as already I have shown you here. This is, as you can see here, this is a machine code. These are the instructions. You can see these are the assembly instructions. So this is a code. So this init is a section which is a chunk of code. And now another the other type is like data. So this RO data is a section name, and this RO data is a chunks of data. This is a data. So this section is a chunk of data, chunks of data. So I have shown you the code and data. So this is a clear definition and clear very clear concept. Now what is a section? Section is a chunk of code and data in an ELF file. So this is the list, and I have shown you 2 examples, one in which I have shown you the code, and in another I have shown you the data. So let's move on to the next slide. In this slide, let's try to understand what is a section header. What is the concept of section headers? So before going into section headers, uh, let's try to compare the conceptual let's try to compare section header with the index of book. So you have already seen the index of a book from your childhood. In the index of book, we have chapter number. We have chapter number 1, 2, 3, and 4, and we have chapter name, like introduction part, then what is a computer, any kind of chapter name can be based on the book topic. So this is a chapter name. Now this is a kind of table in the index of book, like a book index. So this is a chapter name, list of chapter names, and these are the page numbers on which these chapters can be found. So this is a simple idea, and through this concept I will try to compare this concept with the section headers in the next slide. So I think you all know very well this concept of indexing of chapters in a book. You often you have seen in your books in the start of the in the starting pages of any book. These are the very common pages which you can find in every book. So let's see, let's compare this index of book with the section header. As you can see, the chapter numbers, these are the 1, 2, 3, and 4. These are chapter names, and these are the page numbers. So if you have to go to the second chapter, what we can do, we can find the page number first. We can find the page number 25, and then we can read the second chapter from the page number, or we can go to chapter number 4 on page number 60. So this table helps us to find or to jump into specific chapter number. Like this, we have a section header. And in this section header we have the list of sections. These are the list of sections. So as you can see in the top column, this is the name of the table, which is name. So these are the list of names of sections. These are the section names. So these are the section names, and this is the type, and this is the address. These are the memory addresses on which we can find these sections in memory. And this is the offset, which is same as the address, and this is the size. Let's visualize this in the actual scenario. So for example, let's take this example. Like this is init section, and this init section has this chunk of code. This init section has this chunk of code, and where we can find what is the address of this init section. This is the address. This is the address on which we can find this section. So this is the this is just a index. Section header is just an index of the sections. It tells us that where we can find the sections in the memory. So this init can be found at the memory location of 1000. This is the memory location. So in at this memory location, we can jump and find our section, find our section code or section data. So in this case, this is a code of this section. Likewise, we can find the size. As you can see, this is the size. So the size of this section is mentioned here in this particular table, which is 1B. So the size of this section is 27 bytes. This is in hex form. So if we convert it into decimal, we can find that this is 27 bytes. So basically, section header is a kind of table, or you can say it's an index of section, list of sections, from which we can further find our sections. We can search our sections in the ELF file. We can locate our sections in the ELF file like this. So this is the concept of section, what is a section and what is a section header. So this is the section header. Through this indexing of section header, we can find the different sections in our memory. So that's all for now, and I hope you got my point, and through this video you should have a clear understanding of what is a section and what is a section header. In the next video, we will deep dive into section headers and sections. In that, we will find how we will try to do some practicals, like how to find a section, how to fetch a sections, and the other parts of that particular topic. So that's all for now, and I will meet you in the next part. Till then, goodbye. Hello guys, and welcome to the next part of binary analysis tutorial. So in this part, I'm going to show you how you can find sections from the section headers. So let's start. In the last video, I have shown you that what is the concept behind section headers and sections. So let's see what a section looks like in the real binary. So let me first show you how you can dump the section headers, or you can say the list of sections from your binary file. So we will use read ELF, and we are giving wide option to just show the output in wide form, and after that we are using -s for the section headers, and in this case we are using demo. So let's okay. So this is the output of read ELF, output of our demo ELF file. So it tells us that there are 31 section headers. So these are the section names, and the total number of section headers are 31. It means that we have 31 sections in this ELF file. So the one information is clear, that we have 31 sections in our ELF file. How we can find this? We can find from this particular column, which is name column. In this table, the name column has all the list of all the sections, which is like enter p, then node, then all the other parts till here. And these are the numbering, these are the like index number, which is starting from 0 to 30, total of 31. So we have 31 sections, and these are the other informations, other indexes, you can say. These are the other information which RadioLF is giving us in the section headers table. So this is the type. So the type tells us which type of section is this, and this is the address which I already have, like which I have already told you the use of this particular uh, part. So this is the address where we can find the section, and this is the offset. This is the same as our address information, and this is the size. This tells that what is the size of a particular section in the memory, in the ELF file. And after that there is a flag section, sorry, the flag column. In the flag column, these are the flags, and you can find the information of these symbols in the bottom. This is the key to flags. So there is extra information, or you can say there is a special note in the bottom which says that keys to flags means if this key is A, then this means that this is alloc. Alloc means memory allocation. So this A means memory allocation, and this I means like this I is info. So this I means info, means this section contains some kind of information. So likewise you can find this E part, you can find this O part, you can find this X part, like X flag. This X flag is here in these sections, like init, in .text. So these are different flags which are used in every section. So you can like find all these codes, like all these abbreviations here. What does that mean? So these are the list of sections. So let me show you how you can view these sections in the ELF. It's very easy. You can use object dump utility. You can use object dump. So suppose I have to find this init section. I have to find the init section, like I want to view the init section of this ELF binary. So what I have to do is I have to use object dump. So in object dump I will mention that I want to view a section. So I will provide this section option, and then the section name, which is init, and then I want to disassemble. I want the output in disassembly format. So I want to disassemble and then want to see this section in the disassembled form. So I will use -d and then the name of our program file or our ELF file, then hit enter. So as you can see, it is showing this particular section information, like it is showing the chunk of this section, this init section. This is the chunk of this init section. Likewise you can see this is a code. This is a code. This init is a chunk of code in the binary. Likewise you can see the data section in the same way, like object dump section then dot data. I want to see the dot data, and I want to disassemble it, and this is the file. So as you can see here, this is the data. This is our data, which is I think 8 times or 9 times A, and this is also the uh, data bytes. This is the data byte. So this is the data chunk of data of this particular section. This dot data is a section which is a chunk of data. This dot in is a section which contains a chunk of code. We can see we can view the dot text segment, sorry, dot text section also like this. With the same command we will replace this dot data with the text section. As you can see, these are the disassembled code of dot text section. So you can guess this is a code. So this dot text section contains code, the chunk of code. So we can say that this dot text section is a chunk of code in the ELF binary file. Likewise, you can view other sections as well with the same command. You have to replace this part with the section name, and you can find all the information. So that's all for this video. Now I will start explaining the important sections in the next video. Till then, goodbye. So hello everyone, and welcome to the next part of binary analysis tutorial. So in this part I'm going to show you the most important sections of the ELF file. So we have our ELF file, and let me show you, let me dump all the sections of our binary by using readelf utility. So we are giving wide option, and we are giving capital S for a list of sections, and then we have our demo file. We can use demo and hello because we have two files with the same source code, so we can use any of them. So we are using demo file, demo ELF file, and then hit enter. So now we have a list of sections in the section headers, as you can see. So I'm going to explain this part, this .init section, and this .fini section. So this init and this .fini section is important sections in the ELF. The work of these two sections are, if you know the if you have a general idea of object-oriented programming, you know what is constructor and what is destructor. So this init works like a constructor in the program. It executes like it initializes all the code in order to start the execution in the text segment, like in our main function. Like before executing the main function, this initialization must be taken, must be executed. So it is a kind of initialization, or you can say it's in programming languages you can say it's a constructor. And after initializing, then main function will be executed, and when main function will get exited, then this f.fini section will gets called, and it will finishes all the parts of the program. It clean out all the memory area for the ELF file for the execution part. So these two sections are important sections for the proper functioning of ELF. So we can see these sections, like we can see the contents of these sections. Let me show you how you can see this, how you can see this. Let me show you. So we can dump the contents of these two sections with the use of object dump. First we have to provide the option section, and then after we have to put the section name, in this case .init, and after that we want to disassemble, and after that we have to give the we have to mention our ELF file, then hit enter. So as you can see, this is the init content of our section. As you can see, this is init, this is the address on which this init section resides. You can see here this is the same address, this is 1000 and this is also 1000. And if you see here, these are the instructions. These are the instructions which needs to be executed before any code gets executed. So this is just an initialization code. This is just an initialization code. Now let's try to dump the FINI section. Let's clear this and then FINI. As you can see, this is also a code. This is also a code. These are the instructions of finish. You can say FINI means finish. So this is the finish code. So that's all for now. This is only for like this. This video is only for explaining init and .fini. In the next video, I will cover the most important and most used section, which is .text section. So for now, goodbye. I will meet you in the next part. See you. So hello everyone and welcome to the next part of Linux binary analysis. So in the last part, I have explained two sections which were .init and .finish .fini sections. So in this part we will go through a section which is most important, which is .txt, So let me first tell you, this .txt section is the actual executable code. Like these are the actual instructions which gets to be executed by the memory. So this .text section contains our actual code. Our actual code means this actual code. So this .text section contains our code which resides in the main function. So this code, these lines of code is stored in this section, in this .text section area. That is why it is a most important part of a program. So that's .text section. So how we can uh, analyze this section, how we can see this section? So it's very simple. We use object dump hyphen section, and we give the name dot section dot text, and then we want to dump it hyphen d, then our ELF file, and hit enter. As you can see, this section has this section has large amount of data in it. You can see this section has large amount of instruction set, like instructions, you can say code. This section has large amount of code which is executed when the program runs. So these are the actual executable program, like executable instructions in the program. As you can see, the first label is start. So before the main function execution, before going to the main function, like everyone generally everyone thinks that this main function will execute first. The main function is executed first, but the reality is first this start function module is executed first. So this start, what this start does is this start will call the main function. As you can see here, the RDI, if you focus on the RDI register, let's see, this is the RDI register. So this particular address, this is the address of main function. So this particular address is transferred, the main address transferred to the RDI, so that this main function gets executed. So this is actually passing the main function to the RDI, and there is a call. So there is a call to the main function. So it calls the main function, and then the main function gets executed. That call will jump to here, and this main will be executed. So, and there are other parts, but those I will explain you in the next few parts of this module tutorial, of these module tutorials. So that's all for now. The main concept which needs to be explained is the main function and this start function. So that's all for now. I will continue the sections area in the next part. Till then, goodbye. Hello everyone, and welcome to the next part of the binary analysis tutorial. So let's see what is .ro data section, and after that we will see data and BSS sections. So let me open another terminal, and in that terminal we will see and we will compare these data in our binary file. So let's cat our demo.c file and see and let's compare all the data parts with these sections. So this .ro data contains the read-only data. So in our code we have one read-only data, which is hello world. So this hello world resides in this particular section, .ro data section. So basically .ro data section contains the read-only data of our binary. In this case, the read-only data is hello world string. So we can verify this by using object dump, and let's give the section option, and we are interested in RO data section. Now after that we have to give the disassembly option -d, and after that our demo file, then enter. As you can see here, this is the hello world. This is our read only data section data. This is the data. This is the data in hex form, and this is the string, ASCII string, hello world, and this is the address, memory address. So this is RO data section. Whatever you will whatever string you will use in your main function inside main, it will be saved into .ro data section. After .ro data section, we have .data section. What this .data section contains? It contains the global data in our program. So whatever you define globally in your program, that data will be stored in .data section. Let me confirm this by dumping the data section of our binary. As you can see, these are the A's. If you compare with our source code, this is my data, which is 10 bytes of A, like 10 bytes, which is 10 times A character. As you can see, this contains 10 times A data. So this is the address, and these data are these are the program's own data reserved. So basically these are the global data which we initialize in our source file in our program. So this is global data section. So global data is stored in .data section of our binary, and after that we have .bss section. This .bss section is nothing but uninitialized data. So we have one uninitialized data, which is temp, which has 8 bytes. So this temp data doesn't we can't see that this data, because we didn't we have not defined this data till now. When this binary runs in the running state, it will allocate 8 bytes of memory when it will need this data. When it will need this variable, then it will allocate 8 bytes in the memory. If you try to see this data now in binary, then what you will get, let's see what you will get. You will get this, which is 1 2 3 4 5 6, which is 6 byte. So this doesn't mean that this data is actually our data, our defined uninitialized data, because our uninitialized data is of size 8 bytes, and this shows that this is only 6 bytes. So when program runs, then it will allocate 8 bytes dynamically in memory. So this doesn't mean anything to us regarding this part. So this .bss segment contains uninitialized data. So these three sections are important for us. That is why we have discussed it in this video. So next couple of videos will contain all the important sections discussion. So I will meet you in the next part. Till then, goodbye. Hello everyone, and welcome to the next part of Linux binary analysis tutorial. So friends, in this part I am going to explain what is the use of .plt section and .got section. So let's understand this. Let's understand the concept of .plt and .got section step by step. In the first step, we are going to create a simple binary file with some specific options. So let's create a file. Let's create a source file. I'm using Vim editor because my background, my terminal background is white. That is why I'm using Vim editor. So let's create a hello.c program. So let me type a simple code stdi.h int main. Then we are going to print hello world and then return 0. Let's write and exit. Now we are going to compile this hello.c with some specific options. The first option is we are going to compile this into 32-bit binary. So we are using -m32 option. Second option, we are using no pi. Okay, so you also have to compile with the same option in order to follow me. Now rest is the same, our source file hello and our output file hello. Now we have our binary file. Let me show you with the file command. So this is our ELF 32-bit executable, and this is dynamically linked with this particular interpreter. So now let me show you all the section headers of this file, this particular binary file. Let me use a read ELF, and I am using wide option and then -s, capital S for section header, and this is our binary file. So as you can see in the output, these are this ELF file has 29 section headers. It means this has 29 sections. So these are the sections. So in this part we are going to the aim of this video is to clear the concept of .plt section and .got section. So let's try to understand what is the purpose and use of these two sections, because these two sections are very important part in the binary analysis process. So let's see what we can understand. In order to understand, let me first show you my presentation. So let's see what I have in my presentations. So as you already know this simple code. So this is a simple main program in which we have printed hello world. So this hello world, in order to print this hello world, when program executes, when program runs, and when it prints this hello world, it needs the address of this printf function, because this printf function belongs to the C library, and that library is stored somewhere in the operating system. So in order to print this string, it needs the address of this particular printf function, which is uh, nothing but puts function in the library. So the first step is the program has to find out the address of printf function, or you can say puts function, in order to print this. So it needs this address which is in the library. So this is just like, this is just an example. Address can be anything, like address can be changed. Address is like different for different systems. In my case, this is the address. So this is the address which it needs. This printf function needs this address in their program, in this program, in order to print the string. So the next situation is, now the big problem is, now in this situation it needs this address in order to execute this function. This needs to be called, this function needs to be called by using this address. But the problem is, this cannot be called directly. This program cannot call the puts function address directly. So there is a solution for this. So that solution belongs to .plt and .got section. So how? Let's try to understand it. Now we have this particular function which needs the address in order to execute this function. This function needs our program needs the address of this function in order to execute, or in order to print this hello world. So in order to do this, we already have .plt section in our binary file. So what it will does is, it will first request, or it will goes to .plt section. Our program calls first plt section. It will goes to plt section in first step, and after that in plt section our this plt section will give this program an address. As you can see here, jump to somewhere and jump to this address. So this address belongs to somewhere in the memory. So again this program has this address which is given by the plt section. So now now we have this address, and now what we are going to do, we are jumping, because this .plt section shows that this is a jump. It is asking our binary that just jump to this section, this particular address. So when it jumps to this particular address, this address is nothing but the address of this particular section, which is .got. So this address belongs to, or you can say this address is got section address. So this is the address of got section. So we have got the address of got section. Now the program has the got section. Now like this is in this got section, and in this got section has the address of put function, which is stored in the library. So the name is like self-explanatory. .got means global offset table. This is a table where all the library functions addresses are stored. So this got has the address of puts function address of the library, and this program has the address of puts. So now using this address our program can print the hello world. So as you can see, there is a two-step process in order to get the address of this puts function. from the library. How our program goes to .plt section, and this plt section gives the address of the .got section, which is global offset table. And when we reach the .got section, we will get the address of puts address, because this .got section contains the address of put section. So we got the our program gets the address of puts function, and with this address it will call the puts function and print this particular string on the screen. So this is the whole point, like this is the whole concept of using .plt section and .got section. So that's all for now. I will show you all the practical parts in which I will explain. I will show you the plt section and .got section, how they use the addresses in the real time, in the execution environment of the binary. So I will meet in the next part. Till then, goodbye. Hello everyone, and welcome to the next part of binary analysis. So in the previous video I have shown you all the steps involved in which this puts address is accessed by our program by .plt and .got section. So in this video I will explain all these steps by using practical approach. So I will do some practicals on these concepts. So let's see how we can do this. So we have our hello executable, as you can see already. This is an ELF executable, and now I am using GDB to show you all the practicals. Let's use GDB in order to analyze these steps. So gdb-q and then hello. And now let's first set the disassembly flavor to Intel, and then let's disassemble our main function. In the main function you can notice there is a call statement which shows that it calls the puts function, but it calls the put function via plt section. So it shows that it is going to plt section indirectly. It's not going to puts, it's going to puts function, but it is going to pull plt section first. So let's put not now. Let's try to understand this particular area, this particular address. Let's try to examine this area because it is calling this particular address. Let's see what this address has right now. So let's examine three instructions of this particular area. So these are the three instructions. So at this address, you can see this is plt section. Right now we are in plt section at this address, and in this plt section you can see there is a jump there is a jump to somewhere, to some address. This is the address. So at this is jumping to this address. So again, if we try to analyze what this address contains, like again this is jumping somewhere, but this address holds some another address. Let's see what kind of address is this and where it is jumping. So let's examine that part also. So now let's see, again we are using three execution instructions, like execution steps. We are analyzing. I'm not able to pronunciate examine, analyzing. So let's examine three instructions at that particular address. Paste, not this address again. We have to use this address. So you can see this address holds the section of got and like GOT section. This address indicates that this is a GOT and GOT section. So this is jumping to GOT section actually, but there is a mystery here, because right now program is not running. You can see I am like the program is not in running condition. It is stable, it is offline. The program is offline right now. So in offline state, this global offset table doesn't have any kind of dynamic addresses right now. We can verify this, we can clarify this. How? Let's see what this particular address contains, what this particular address contains, like what this address holds. Like this address is holding something. Let's see what it contains. So in order to see, let's see what it holds. As you can see, this particular address holds this particular area. You can see, and if you notice, this 56, this 804956 is nothing but it is pointing to the next instruction. This address is same as this address, and this address is came from this jump address. Indirectly it is jumping to the next line. Now this jump belongs to the got entry, means this is jumping to the global offset table GOT, but again this GOT is redirecting the instruction to, like redirecting the program to this particular line, because it is showing already that this is the same address as this contains the address of the next line in the PLT section. So indirectly right now the program is not in the running state, it is offline, and in the offline state this GOT doesn't have the address of puts. That is why it is jumping right next to the line, like it is jumping right here via our global offset table entry, like our GOT. So this doesn't make any sense, because our call doesn't gets the puts address in this case. Why? Because program is not running. So let's try to run the program. So now let's disassemble the main again, and let's try to put a breakpoint after the call function, after the call of puts at PLT. So let's put a breakpoint at this address after the call. So let's use B, and then sorry, B and this address, and then run the program. Okay, so now programming is running and it has already printed hello world, but we have paused at this location. So now, so that we can analyze the program, analyze all the steps. So first part is we have, let's examine three instructions at this particular location. As you can see, again this is the address, which is 804C0110. So it is jumping to this address, and in the previous part, we have seen that this particular address is corresponding to the next line. Like this address corresponds or jumps, this line is just jumping here when the program is not running. Now program is running, so let's find out where this address is going. So in order to do that, let's use this examine command, and let's copy this and paste it, and let's see what the address is. Now this is the address. Now this address belong to this particular section, which is .got got section. So this is pointing to got section, and in got section this has the address of F7DE4260. Now this must be the address of puts function, because now this is not belonging to this address. In the previous state we have seen that it was redirecting the instruction to, like redirecting the code flow to this particular area, but right now it is showing the address, like this is showing different address, which is this. So let me show you what this address is. If we see, if you want to view the address of puts function, then we can use info command, info functions and puts. So the puts address is this F7DE4260. If you see carefully, if you trace carefully here, you can see that this address is 47DE4260. This is the same address. This is the same address. So this is pointing to the address which is puts address. This is pointing to the got section, and got section is giving the address of puts function. So that situation, that scenario is explained here. Like I have explained you the scenario which I have, like in my previous video, which I have shown you already, that first the call is made to the PLT section, and then this PLT section will forward the call to got section, and this got section has the address of puts function. Via this particular address, the function gets called, and then our string gets printed. So this is the chain of execution. This is the way the binary calls the puts function via the PLT section and GOT section. First it will call the PLT section, in which there is a jump which indicates that it is jumping to the GOT section, and after the jump, the GOT section has the address of puts function. So through this it will get the puts address in memory, and it will successfully executes and prints the hello world. So that's the main reason why PLT and why there is PLT and GOT section, global offset table section in the ELF file. So that's all for now. I will meet you in the next part with a new topic. Till then, goodbye. So hello everyone, and welcome to the next part of binary analysis. So in this part we are focusing on understanding the two sections, which is .rel .dynamic and .rel .plt. So these two sections are responsible for storing the addresses which are used for relocations when the binary runs. So in single line we can say that these two sections contains the information used by the linker for performing relocations. So what kind of information they hold? So basically they hold the addresses of library functions. The addresses of library functions. So these are the library functions. You can see this is the put function, which has the address offset this, and this is the libc start main, which has the address of this. So these are actually these are the addresses which are used in the runtime when the ELF binary needs the address of puts in order to print the hello world string. Then it has to access this address. It needs this the program needs this particular address in memory where this puts belong. So where this program will find the addresses from these two sections. The first one is dynamic and second one is PLT. So this is the dynamic section. Like this there are two like sections. The first one is dynamic, the second one is PLT. So basically these two sections hold the address table for relocations. That's all. That's the only purpose of these two sections. So that's it. That's all for now. I will meet you in the next part with the next videos. Till then, goodbye. Hello everyone, and welcome to the next part of binary analysis. So in this part we are going to understand .init array and .fini array, or we can say finish array. So these two arrays are data sections. Like there are data stored in these sections, not any kind of code, only data. So these sections contains the function pointer addresses. So what kind of addresses these are? So first let's understand what is the purpose and what are these sections. So by definition, the init array section contains an array of pointers to functions to use as constructors. So basically, as the name explains everything, this is init. Init means initialization array, and fini means dot finish array, which is a kind of destructor, or you can say this is destructor. So basically, if you have uh, general idea of object oriented programming, there are constructors used in the program and destructors also used. If you don't use constructors and destructors, by default program uses its own constructors and destructors by default. So these are those constructors and destructors in the ELF program. So these contains only the addresses of those constructors and destructors labels. So we can see those addresses in ELF. Let's see how these addresses looks like and how these functions are looks like. So let me first disassemble our ELF binary by using -d option and then hello, and let's see. So this is the disassembled code. Now as you can see, we have different labels here. So let's see. Okay, now let me first show you what is the data stored in these init section, init array section. So for that we will use object dump -d, and we will provide a section, and what section we are interested in, init array, and we provide our ELF file. So this is our init array section, which is a kind of constructor, and it holds the pointer address. It holds the data, which is a kind of pointer, which indicates or which is an address of constructor. So this address belongs to the constructor, and where is this constructor? This is the frame dummy. So this constructor or this frame dummy is actually executed before the main function gets executed. When the program is loaded, it loads frame dummy first as a constructor in the ELF. So this frame dummy, if you notice, this is the address, and this address belongs to this particular line of code. You can see the first, this is 70, this is 70, that the next one is 91, the next one is 91, then 04, then 04, then 08, then 08. So this is actually the address which is pointing to the frame dummy, which is a kind of constructor. As you can see, initialization part of the binary. So this is the initialization part, which basically this section contains the data, and what kind of data? This is actually an address pointer which points to this frame dummy section, frame dummy label, you can say, which needs to be loaded before the main function loads. So the next section is like fini fin array. This is kind of destructor. So if we try to find this particular address, so you can see this is the destructor label in our disassembly. you can see the address. Just trace the address. This is 08, the first part is 08, then 04, this is the 04, then next part is 91, which is here 91, then after 40. So this is the destructor label. Destructor label, like destructors are used after program, like before program exits, the program calls the destructor function. So this is a destructor, and this fin array contains the pointer address of this destructor function, you can say function. So these two holds the address of initialization and destructor address pointers. So that's all for now. These two sections belong to these two functions, which is a kind of constructor and destructors in the ELF binary. So that's all for now. I will meet you in the next part. Till then, goodbye. Hello everyone, and welcome to the next part of binary analysis tutorial. In this part, I will explain you these three sections. So let's start. So the first section is .symtable, which is .symtab section. This section contains the symbol table, which is a table of function or variable in ELF file. So as you can see here, this is the output of section header table of our hello binary, and this is the sim table, means symbolic table. And if you want to see the symbolic table, then you can fire this command, read elf hyphen small s and then elf. Then you will get all the symbolic table names. So these are the symbolic table names. In this table you can see these are the symbols, like these are the strings and these are the values. So basically these are the like strings. These strings are used in the binary while it is executing or while it is in static state. So they usually there are two symbolic table sections. The one is dynamic symbols, which is, you can see here, this is dynamic symbol table. Dynamic symbol table used when the program is in running state. So these symbols are used when the program is in the running state. So as you can see, these are the functions and variable names. So these are the tables which contains function and names. So as you can see here, in this table, the table of like SYM table, in this table you can see these are the functions, either these are functions or these are variables. So these are the combination of functions and variables in this particular section, which are used when the binary runs in the memory. So we usually there are two tables here, which is dynamic symbol and sim tab. So this is the sim tab and this is the dynamic symbol tab. So this dynamic symbol is also shown here in the output. So let's move on to the next section, which is str tab, which is string table. Now this string table contains the strings only. So this string tab actually contains the string. So these are the strings. Now in the previous slide you can see these strings are the same as these string. If you compare, this is the list of the strings which are function and variable names, and these names are stored in this particular section, which is string table. So string table section contains string containing the symbolic names. So these are the symbolic names, and these names are stored in the str tab section. Now moving on to the next slide. So the next section is .shstr table, which is nothing but sh is for section header and str for string and tab for table. So section header string table means this section contains all these names of section header. So this particular section contains all the names of these strings in the section header, section string table. So as you can see, we can see the section header string table. So these are the list which is same, as you can see here. These also these are the same names which you can see here. So this is actually strings. This is strings of section header table. So basically these four symbolic table, string table, section header string table, these all are contain strings which are used, like these are the symbolic names for the program which is used in the processing when program runs in memory, then these are used in that program. And there is also one more left, which is dynamic string. Then I have covered dynamic symbol table and dynamic strings. So these two are almost the same thing. These two contains the strings, but in dynamic symbol there are symbols, and in dynamic strings there are dynamic strings which is used while program is running. So how we can see these dynamic strings and dynamic symbol? Usually we cannot see when the program is not running. You will not get any particular proper results in dynamic section, like dynamic sections. So this dyn shows that these sections are dynamic, and sym means symbol. So dynamic symbol and dynamic strings, basically these symbols and strings are used when program runs. So when program runs, if you want to analyze these sections, you have to run the program first and then analyze these types of strings. So I will cover these things when we cover the analysis part. When we take a binary file, then we will deep dive into the analysis of that particular binary to get all the information. So in this part, this is just an introduction about these sections. So these are the commands through which you can see these sections. Like you can use -p option, and then the string name, section name. Let me show you by giving an example. So we have a binary which is hello, and this binary has these sections. Okay, so let me show you these sections first, these three sections first. So for viewing these sections, we use readelf again, and we will provide -p option, and this -p option is used for dumping the strings of the sections. So we have to mention the section name here, like symtab, and then our binary file. As you can see, this is symbolic table .sym tab. So this is symbolic table, and this symbolic table contains these kinds of data. Okay, So this is symbolic table. In the in the presentation, as you can see, these the symbolic table contains a symbol table, which is a table of functions and variables. So through this command we cannot see those variables and functions names. So how can we see that? We can use hyphen, not t, but we can use another command, like let me show you. This is not the command by which we can see the symbolic table, because symbolic table can be viewed by using different commands. So in this case we can use hyphen. Let me see in our presentation what I have used. So okay, so we have to use, let me show you the help section of the ELF, read ELF file, read ELF utility. So in this help, you can see, if we want to display the symbol table, focus here. If we want to see the symbol table, we have to use this option, hyphen syms, and this is also this is a symbol table, sym tab. So this is the same. So we can use hyphen s for viewing the symbol table. Okay, so now let me use read elf, then hyphen s, and then our binary file. So as you can see, these are the symbols. Actually these are the strings, which is nothing but combination, like a combination of variables and functions which is used in the program. So as you can see, these are the these are the strings. As if you see carefully, there is main, the name of our main function, which is main, start, and like this puts. And in the dynamic section you can see this put name, which is our function name of puts. So basically you can see the symbol table by using the hyphen s command. Now like this, we have to use a different option, hyphen p, for viewing string table. So if you want to see the string table, when we have to mention str tab and then our binary file. As you can see, it has dumped all the strings of string table. So these are the string table. These are the same strings which we have dumped in our previous command with dynamic, like symbol table. So these are the same symbols, these are the same data, like the same strings. As you can see, this is the main. So basically this is just string table. Now the next one is section header string table. We will use the same part, but we will mention sh section header and str tab. So in this part, in this output, you can see this is section header string table, which is nothing but these strings. So these are the strings, which is symbol table, string table, section header string table, then all the other section headers, like section names. These are the section names. So this is a list of section names which resides in section header string table section. So that's all for now. This is in this video I have finished, or I have completed the section headers part. So in the next video I will explain about uh, program header. So till then, goodbye to all of you. Hello everyone, and welcome to the next part of binary analysis tutorial. So in this part I'm going to investigate this particular binary file, which is simply a demo which just prints the hello world string, and this is 64-bit binary. So I will examine, or I will investigate by using the concept of cross reference checking with the hex byte of our binary. So it's very interesting part. You will see how these data is like how these data are converted into some kind of hexadecimal codes in the ELF binary, which looks very interesting if you see carefully. And let's start. So this is our section header of this binary. These are the section headers, and if you notice, it is showing that the offset is starting like this section headers is starting from this particular location in the ELF file. So this is the address where the section header information is starting. So this is the address from where these information is starting. So let's filter out this particular address with the hex dump utility, and let's cross check every information one by one. So let me first dump the binary, hex dump -c, then space demo or ELF file. Then we are grepping, and then I am interested in I'm interested in 4 lines only, not 4, but we can see we can dump 8 lines. You can see not 8 but 7 lines. So what we are going to search, we are going to search this particular address, which is 3690. So wherever you find 3690, show me, and then after finding, show me 8 lines after that. So it has found this particular memory address, which is 3690, as you can see. So from this address the section header information is starting. So let's start one by one. So the first part is like this is null part, name, then null, type is null, then all the parts, all the fields are actually 0. So there is no, like there is nothing here. So that is why it's all showing 0, and in the next line it is also like marking this star. So actually these two lines indicates these two line indicates this first line part, which is nothing but 0, and after that this line, notice on this line, this is showing some kind of values, some kind of hexadecimal data. So let's start by going through these hexadecimal bytes one by one. So this first byte 1b, this first byte 1b shows the name, like name, the type of section. So in this case this is .enter p type of section. So .enter p section is denoted by this particular hexadecimal value, which is 1b. So these first 4 bytes, so these 4 bytes holds the information of name, section name. So these information is indicated by these 4 bytes. So the next part is let's see what the next byte shows us. So the next 4 bytes shows the type. What is the type of the section, which is in this case proc bits, and proc bits has a hex value of 0 1. So this is the hex value, like this is a special code which is indicating that this is of type proc bits. So this will be changed in the next part of, like in the next section, which is a note. We will see that. So in this case, these 4 bytes indicates this type information. Now the first 4 byte indicates the section name type, which kind of section is this, and the next 4 bytes shows the program bits, like proc bits, these next 4 bytes. And after that we have another 8 bytes. We have a group of 8 bytes, and these 8 byte holds the information of flag. Notice this flag information is these 8 bytes. So in this 8 bytes, this 02 indicates the flag data, which is A, and A is alloc. So alloc is indicated by 02. Okay, right? So this 02 indicates the flag value, which is A, and these 8 bytes are reserved for flag section, this flag data, flag column, you can say. After that, the next 8 bytes, after that these 8 bytes shows the address of this particular section. So this enter P address is 318. You can see 03 and this 18. So these 8 bytes shows the address of section. This is the section, like address of the section. So these 8 bytes hold the address part, and after that we have another 8 bytes. So these 8 bytes are nothing but the offset, this offset part, and after that we have again the whole 8 byte, which is which shows the size. As you can see, 1C. You can notice this 1C. This is the size section. So these 8 bytes holds the size area, like size part, and after that we have another 4 byte. The next 4 byte shows the LK, the LK you can say section, or you can say information. So this LK information holds these 4 bytes. In this case it is 0, and these all bytes are 0. So if there is any kind of data, like if there is a digit which is other than 0, then it will reflect here. Okay, so these 4 bytes are reserved for LK, and the next 4 bytes indicates the INF part, this INF part, which is again 0. Now the next 8 bytes, shows this alignment, like AL part. As you can see, this is 0 1, and here it is 1. So this 8 bytes holds the AL information. which is alignment. I hope this is alignment one, like value, and this 8 byte shows the information regarding this AL part. And after that, the last 8 byte in this whole line holds the information of this ES part, this ES section, which is again 0 in this situation. So this ES is nothing but this 8 byte. So if you calculate there are 64 bytes. So this whole line takes 64 bytes in the ELF in order to store the information, of this particular one section. This particular line holds the area of 64 bytes in the ELF. So this 64 bytes holds the information of this particular one line. So in the next part, this is different, like this is different kind of section, which is note.gnu property. So as you can see here, this is 23. Now the first 4 byte is reserved for this area, and in this case it is 23, and in our previous section name it is enter p, which was 1b. In this case this is 23. So this 4 byte is reserved for this area, and the next 4 byte is nothing but this type, which is 707, and in previous part we have seen that it was proc bits, and which has the value 01. In this case this is 07, which indicates this is note type section. So likewise you can like trace out byte by byte, and you can find all these data inside this particular hex dump. You can trace out the whole ELF bytes one by one, and you can make notes of like how these information is encoded in this particular binary, and how these bytes holds different kinds of information regarding these sections and all the different kinds of information. So that's all for now. My aim was to give you a general idea of how you can cross reference, or how you can investigate the different data in your binary with this method. So that's all for now. I will meet you in the next part. Till then, goodbye. Hello everyone, and welcome to the binary analysis tutorial course. And in this part we will look at program header section, not a section but part of ELF binary. So let's see what is program header in ELF binary file. So as you can see here, we have 4 parts of an ELF normally, and the first one is executable header, second one is program header, section, and section header. We have already covered these section header and executable header. Now the last part which is left is program header. So we will try to understand what is a program header, what is the work of program headers in this video. So basically program header is used by the OS and dynamic linker to locate code and data in virtual memory. Because let me first tell you what is a program header. Actually, program headers is a chunk of segments, a group of segments uh, which contains these sections. This program headers contain sections, but in a grouped way, in a segmented way. So why these sections will be grouped in program headers? Because program header is used means segments. These segments used by the operating system and dynamic linker to locate data and code in virtual memory. Now if we differentiate section and program header, we can easily understand the difference between these two. Now the section is for static linking only in the binary file. Sections are made for static linking, not for dynamic linking, but program header is used for the dynamic linking, or you can say this is used by the dynamic linker and the operating system to actually locate code and data in virtual memory in order to run the binary. So basically program header, the need of program header is when the ELF executes. When ELF file executes, then the program header is used. This is used for dynamic linking by the dynamic linker. So let me again clear this, that group of sections is like a group of sections called chunks, small chunks called segments, and these segments are program headers. So the group of sections combined together which makes segments, and these segments are called program headers, which is used by the dynamic linker to locate code and data in virtual memory when it is executed. So let's see the practical, let's see what program header looks like in the ELF binary with some practicals. So as you can see on my screen, we have two binary, hello and demo. These both are like same binary. The only difference is demo is 64-bit and hello is 32-bit version. So let me show you the 64-bit version. Let's see the sections part first. Let me dump this section part first using capital S and then demo. So these are the sections. I think you already knows what is a section. So these are the sections. There are 11 section headers, and let me show you the program headers of this file, this binary file. So for viewing program headers, we will use hyphen L, I think, hyphen L. We use wide option, hyphen L, and our binary file. Okay, so use hyphen L for viewing the program header. So as you can see, the output is saying that the entry point is this, and there are 13 program headers. There are 13 program headers, means there are 13 segments. So there are 13 groups, you can say, and in those 13 groups these sections are divided. These total 31 sections are there. So these 31 sections are divided into some group, and those groups are called program headers. So these 11 section headers are divided into 13 groups. You can see here 13 groups. So these 31 section headers are grouped into 31 segments, and these are the groups. So you can see segments. Here you can see that it is showing that section to segment mapping means these sections are grouped, or you can say mapped into segments. So you can see these are the sections which are grouped. These are the sections which are grouped, and these are 13 groups, means 13 segments group of 13 segments, which is called program headers. So there are 13 segments, or you can say groups, in which these 31 sections are divided. I think now it's clear to you what does these program headers contain. These program headers are nothing but segments. So we have 13 sections. These are the list of 13 sections. These are the type of these are the type of segments, not sections. Sorry. These are 13 segments. There are 13 program headers, which are these 13 program headers, and these headers have a name. Like these program headers have a name. Like first one is PHDR, means program header. Second one is interp means interpreter. So these are program headers. These are the type. Which type of program headers are these? So these are the load, and then dynamic, then node, then GNU property, then EH frame, stack, and the most important part, or the most important information in this table is this interp. This interp is interpreter. The need of this interp segment is when the program needs to map the addresses. When program runs, it is needed to map all the variables and functions into memory from the library. In that case, this interpreter is needed. In this case, it is showing the location of the interpreter which is used in this case. So this is the interpreter name. And after that, the most important part is the most important column here is this flag. This flag shows the permission of these segments, like R for reading, E for execution. R for read, E for execute, W for write. So these segments have a read and write permission, read, execute, and write permissions accordingly. So as you can see, we have one segment load which has read and executable permission. So this load is responsible for our binary execution, because this particular segment has the code section, executable code section. And let me first clear you all the let me first tell you and explain you what are these informations. So these are like, the first one is like offset. This is the address of these segments on which these will start in memory. This is the virtual address, this is the physical address, this is the file size, what is the size of the file, this is memory size, and this is a flag, and this is the alignment. So the important part in which, like, the most important pieces of information which we will need in future in the coming sessions is this flag part, this flag. So these are the, like, flags which has read, write and execute permissions of these segments, and in these segments this load segment is very important. Now let's try to understand, let's try to correlate these segments with these mappings. So you can see the segments are starting from the 0 count, 0, 1, then 2. So you can see our, like, the segment which has executable permission is like R and E for executable. So this is our main code, this is our main executable code, where it, like, where it resides in memory in our binary file. So let me correlate this load with these sections. So if you count the segment, this program segment, the program header segments, it is starting from here. So this is our 0, this is 1, this is 2, this is 3, this is 4. So if you see in the third part, in the third segment, we have read and execute permissions. So if you follow the same count here, 0, 1, 2 and 3. Now in the third part we have .init. .init means this is a kind of constructor, or you can say initialization. And after the .plt, I already told you what is the purpose of .plt, then .plt.got, then .plt.sec, then .text. The important part here is .text. This .text contains our actual executable code, our main function which we want to execute. Now the purpose of the program is stored here. The purpose of our program is, like, the main code of our program stored here. So this particular instructions, or you can say code, the main code resides here between these memory locations. When this program loads, the memory area will be this, the virtual address. This is the memory area on which the program loads in virtual memory. And this load segment contains the .text section, which has all the executable code segment. So this is all, like, this particular segment 03, which is load segment, contains all the executable code. As you can see, this is the initialization, and in the last you can see this is .fini, which is kind of destructor finish. And in between these are the .plt and plt.got section, which are used for function address mapping. I already, like, explained, or we have already seen this. After that, the fourth index segment, which is here. After that, this is the fourth. If you count 0, 1, 2, 3 and 4, this is the fourth segment of program header. It contains .ro data, read-only data, EH frame and all other parts. So this contains our read-only data. Read-only data means our string, which is hello world, which has to be printed. Then after we have init array, and then again we have one important part, one important segment, which is dynamic. So you can see, if you map it, or you can correlate it like this part 06, which is dynamic. You can see here, this is also dynamic segment. The name of the like the type of header is dynamic. So this is the dynamic section, which is read write permission, which has read write permission, and which has these virtual addresses. This is the physical address, and this is the virtual address. And rest are like these parts. So the important part, I have already told you, the load section, which loads our main code. And after that, there are other segments which are also important. So we will see that in the coming sessions, whenever these other parts are used, we will see that. So for now, you should have a clear like understanding of what program header is, what is a segment, what are the segments in program headers, and where the executable, where you can, like, how you can find the executable segment in the program header by viewing the flag column and tracing that that particular segment is particular segment should be executable. And that's all for now. This is actually just an introduction for program header. In the coming part, we will do some serious practicals on binary analysis. So through this tutorial, like it's a kind of journey, I have explained all the four parts of ELF binary. I have covered executable header, I have covered program header, I have covered section and section headers. So I have covered almost all the four parts of ELF. So I think it, like, all the concepts are clear now. And after this, now we know that ELF has four parts, and each part, what is the purpose of each parts, like what is the purpose of each part, and how we can use them with the help of tools, how we can view them, how we can analyze their data in memory. So I think now we are ready to deep dive into the investigation process, or you can say analysis process, actual analysis process of binary, of any kind of random binary. So we will start from the next video, in which we will look at some binary, and we will see, or we will find different kinds of like information, hidden information in there. Till then, goodbye, and I will meet you in the next part. Goodbye. Hello everyone, and welcome to the next module, which is module 3. So friends, in this module we are going to learn how to analyze the binary file, the basic analysis process. So we will deep dive into the analysis process. Till now we have studied the basic file format of ELF. Now it's time to do some analysis part. So this is the first part of analysis, binary analysis, and in this part we are going to use some basic tools, how to use them in order to investigate any kind of ELF binary file. So let's see what I have in this part for you. So this is the simple situation where it is a kind of scenario. It's a challenge scenario where suppose you are in a team of investigations, like you are in a team of forensic investigations, and your team have got a file from somewhere. So this is the top secret file they got from somewhere from the internet, and they have sent you this file and told you that you have to find out what kind of secret is in this file. So you have to go through the process of analysis in order to find the secrets in this file. So what is the basic process? What is the first few steps through which you can find or you can investigate any kind of ELF binary file? So this is the situation, and you have to find the secret which is stored in this file. So they are not able to find that particular information in this file, and they are handed this file to you. So it's your turn to show your skills in order to find out the top secret in this file. So let's see how you we can do the investigation process, or you can say analysis process of this file. So now the first step is, if you have any kind of file and you need to investigate that file, the first process is you have to determine which kind of file it is by using file command. You have to use file command first in order to determine the type of file. So file space, and this is our like target file, which is top secret. So let's see what kind of file it is. This shows that this is an ASCII text. So maybe the secret information is stored in this ASCII text form. So you can see you can do cat and top secret. Now this is just alphanumeric characters with symbol, some special symbols. So there is nothing you can you can't guess what kind of secret information is this in this like random alphanumeric characters. So it seems that this maybe this file is encoded into some kind of encoder, like this is some kind of encoding. So what we can do, the first initial step is the first point in our mind should be that maybe it is encoded with base 64. So it's a guess, it should be our first guess that maybe it is encoded with 64 base 64 encoding. So let's try to decode this file with base 64 decoding. So we use base 64 and then -d for decoding, and we use this file top secret, and I am redirecting the output to a new file called file decoded file, decoded, then file, enter. So we have our decoded file. Now let's see what this decoded file, what is the type of this decoded file. So file space and then decoded file. As you can see, this decoded data is of zip archive data. This is a zip archive data. So this is our first step. Like the first step is completed. We have we found the type of the file, like which is a zip file. This zip file is encoded with base 64. That is why it was showing some garbage alphanumeric digits or characters. So this is a zip archive data. Now what we can do with this zip data, we can extract this zip file with zip unzip command. So we will use unzip space and then our zip our decoded file. So we are unzipping this file. Let's see what it will gives. It has extracted, and this extract, like this zip has given us two files. The one is just a number, like kind of it is a kind of file, and the second one is top secret. So let's ls to see what kind of file we have. So there is top secret, one is top secret, and the second one is this particular numeric kind of name file. So what we can do with these two, one is like binary file. It is a binary file because it is in green color. So we can confirm that file, then top secret. So this is an ELF 64-bit executable file, and the second one is, let me find out which kind of file it is. 87. So it is an PNG image data. This is like some kind of image file. So let's first run this top secret. What is this, like how it runs? Let me see. Top secret, then like it is asking for some kind of password. So let me give some random value. This is wrong. Okay, so it is it is expecting some kind of password which we don't have right now. So maybe this PNG image data is, maybe this image contains some kind of secret. So we can confirm that, like we can see that file. So this is our image file, as you can see, 875467. So this is our image file. So let me open this file. So I have opened, and this is our file, like this is our content in this file, which is password is secret. So it has shown that like it is giving us the password, and in this case the password is secret, secret, secret. If we enter the secret, and we got the right answer, and here is the secret key. So this is the secret key, and we have got the secret key from this file. So you can see these are the process, like the initial steps through which we have got the, like we have got our secret information from a base 64 encoded file. So the file was encoded in base 64, and we have decoded first to get the actual data. After decoding, we found zip archived. We found the zip archive data, and then we have unzipped that data, and we have got two files. We have like extracted two files, and in these two files, the first file was an image file which got the password, and we have used that password with this binary file, and we have got the secret. So in this part, what we have learned, that we always use file command first to find the type of data first. What kind of file is this? And after that, we perform some like some steps and those steps is defined by the type of file, like what kind of step we will take. It depends on the file type. If it was some kind of like it was if it was a different kind of file after the decoding, then we should have performed some different kind of actions. So I will perform every kind of actions, like every kind of steps in the coming parts. So these are the first and most simple steps which is followed, which should be followed at first. So I will meet in the next part with a new, like with a new kind of challenge in the investigation process, or you can say analysis process in ELF binary. Till then, goodbye. Hello guys, and welcome to the next part of binary analysis tutorial series. So guys, in this part we are going to take another challenge in which we will learn something new. So let's jump into the challenge. As you can see on my screen, we have a file called challenge2, and we have to solve this challenge. So through solving the challenges, we will learn different tools, how to use them in order to investigate our binary files. So in that way we will learn more about tools, how these tools can be used in binary analysis process. So let's start to solve our challenges. So this is a file. First we have to check the type of file. Which type of file is this, by using file command. So file space and then our file name. Again, this is an ASCII text. So let me cat this so that we can see the ASCII text. Again, this garbage type of, like this, then this nonsense type characters are shown, but this, again, this is showing us the clue that it may be base 64 encoded data. So let's try to decode this so that we can see the file. So let's try to decode. So how can we decode this? We can use base 64 -d option, and we have to provide our file name, and we have to redirect the output into new file. Let's see our new file. So we have our new file which may be decoded, which may be in the decoded form. We are not sure about this new file. So first let's check it again by using file command, file, new file, and as you can see, again this is zip file. So this is same, these are the same steps as in our previous video, but after that all these steps will be different. Okay, so let's see how it can be. So this is a zip file. So now what we have to do is we have to unzip it first. So unzip, use unzip command, unzip, then new file, and hit enter. So it has extracted two files. One is test, the second one is b1. So it has given us two files. So this b1 and this test file, and this test is in green color, and this green color shows that it is an executable file. On the other hand, we have b1 file, which is not kind of like this doesn't look like it is an executable file. But let me check by using ls command. So as you can see, this test has read, write and execute permissions, which shows that we can run this file. And the b1 file is just a read and write read and write permissions. So what we can do first, we can run this test file so that we can understand what is the behavior of this test file. So we are in protected environment in our virtual machines, so it's not a risk to run this file because we are in the virtual environment, so we can run this file. So let's run this test file. As you can see, error while loading shared libraries, and this libconfidential.so. So it is showing that there is an error while loading the shared library. So this test needs a shared library file to successfully run this, to execute this test file. So it needs libconfidential.so file, which is shared object file. So without this file cannot be opened, this file cannot be run. So and it is also saying that no such file or directory, means it doesn't find this file, this shared object file, in anywhere. So as you can see, we don't have any libconfidential.so file, and this zip file has given us only two files, which is b1 and this test. So let's try to investigate the second file, which is b1. Let's try to see what kind of file is this. So we use file command, file, then b1 file name, and as you can see, this is showing that this is png image data. This is an image file, png image file, which has the resolution 132 into 24, which is very low resolution. So we can first we can see the image data, then after that we will decide what we can do with this file. So let's open the file manager. Let's see our let's see our document. I'm going into my directory for the moment. So this is the directory, this is the same directory which I have opened in my Dolphin file explorer. As you can see, this b1 is png image data file. So this is an image file, and this image if you open this image file, it is showing that only one message, hidden in me. So this is a kind of clue which it is giving us, because I have made this challenge for you to understand the basic working of the binary, and in this way you can learn different tools, how to use them while investigating the binary. So this image is showing that hidden in me, something is there in this image. So how can we find this? How we can investigate further? So let's try to investigate further. So now what we can do, we can check again. So our task is to run this file. So the only way to run this test file is, first we have to find the library file, because if we try to investigate the library file with ldd command, we can this command shows that this is the file, this is the exact file which is not found by the test file, by this executable file. Rest of the library files are found, but only one library file is missing, and this library files is needed in order to run this test file. So let's try to find this file. So we have only one option to look at, which is b1. This b1 file is suspected, so let's see how we can look into that file and try to investigate and try to find that library file. So first let me use hex dump. So this hex dump will dump all the hexadecimal bytes of b1. So let's try to see the hexadecimal dumps. So as you can see, I am using less command to see the dump. As you can see, this file is starting from this byte, this particular hex byte, which is .png, which shows that this is a png data file. So these are the bytes. So these are the magic bytes. First 4 bytes are the magic bytes, in which the very first byte is magic byte, and the rest 3 are the rest 3 bytes shows the particular file type extension, which is in this case png, and rest are the bytes, as usual, normal bytes. So what we can do is, first we are thinking there is logically we are thinking that maybe in this particular image file, maybe somewhere is hidden, like the library files of this test files library file is stored somewhere in b1. So it can be possible that this particular test library file is stored somewhere in this b1 file, b1 image file. So how we can sure, how we can find, how we can test that maybe that file contains our shared object file of the test. So how we can do this? We can again use hex dump. So hex dump space and -c, then b1. Then now this time I am using grep command, and I am filtering elf. Because this elf, if there is an elf character in this b1 file, image file, then there is a possibility that that library file is stored somewhere in this image file. So let's see. As you can see, this elf is existing in this particular b1 file. Somewhere is written .elf in hex. So as you know, in the all the binary files have this particular magic bytes in them. So 7f, 45, 4c and 46, this is the magic bytes which is showing in this b1 hex dump. So what we can do now, we can actually extract these bytes. We can extract these bytes from here, from the address where these bytes are starting in this particular image file, which is b1. So we can extract these bytes till the end. After that, we will test this particular binary file. If we successfully extracted, and if then we will check if this file is like valid or not, like these bytes are valid or not. So first uh, let me extract these bytes from this image. So how we can do this, we can actually use our dd command, dd utility. Through this dd utility, I am going to extract the bytes from this location, this address, till the end of the file, till the end of b1. So let's do this first. So first let me use skip. So we have to skip. So before skipping, like before using dd command, we need to find the exact location from which these bytes are starting. So how we can find this? So we can find this by using printf function, and in that printf we are giving %d, because because we need the values in decimal, and these values are in hexadecimal. So we are going to convert these 6A0 value into decimal. So let's give this 6A0. So the output is 1696. So after 1696 bytes, these elf.elf bytes are starting. So from this location we are going to extract the whole byte to a new file. So let's extract this with the dd command. So dd skip is equal to, skip means from where we are going to dump all the bytes from, in which location do you want to start the extracting, start to extract the bytes. So the location is 1696. So after 1696, then what we need to do is we have to mention our input file, which is in this case b1, and then output file name, which is of means output file. So we are going to give b2, and after that we have to mention bs, which is by 1. Then we have to enter. Now these records in and out, then this is like copied, like we have copied all the, like we have extracted these bytes into our b2 file. Now we have a new file called b2. Now let us confirm that these bytes are actually what kind of file is this. So file space and b2. So as you can see, the file output shows that this is an ELF 64-bit LSB shared object. This is a shared object file, and this test binary file needs a share object file in order to run. So what we can do, we can test again, like we can run test file again, so that we can test that if it is successfully running or not. So hit enter. again it is saying that error while loading shared shared libraries, this particular. So let me first rename the file. Let me first rename the b2 file into this particular libconfidential.so. But before that we use a readelf. We are going to use readelf so that we can confirm that this is a library file, this is a shared library file, by using -f command to see the headers. So -h and then b2. As you can see, all the information is shown correctly. This is an elf64, then all these things, and in the type section you can see that this is an shared object file. This is a shared object file. So we have confirmed that this is actually an shared object file, and now what we can do is we have to rename the file, rename the b2 file which we have extracted from dd command. But before that, let me show you again what is the name of the file, what is the shared object name, what is the library file name which we need to rename. So let me rename b2 to libconfidential.so file, libconfidential.so file. So now we have libconfidential.so file, which is the library file which this test is needed in order to run. So let's try to run again. It is giving that this cannot be opened and there is no such file or directory. So what we have to do is we have to provide the proper path. We have to tell this test file, this test binary file, that what is the correct path of this particular library file. So in order to tell the test what is the proper path of this libconfidential.so file is, we will use this export command, export, and then ld underscore this environment variable, which is ld and library path, then we will tell that the library path would be the current directory, current location, which is again pwd, means present working directory, and after that we have to mention again ld library environment variable, ld library path. So in this way we are giving the exact location to the ld library path, so that if this particular binary calls the library path to run the binary, to run itself, then it can find the library file in this particular path, like which is right now in the current directory. The library is in current directory, library file is in current directory, which is pwd, present working directory. So we have successfully exported the value in ld library path environment variable. And now if we again test the binary file with ldd, let's see what will be the output. As you can see now, the dependency is solved now. Now this particular file location is showing in our current directory by the LDD. So let me run this test file again, and let's see if we can run it successfully or not. So it's executed successfully, which is like confidential information, and this is very secret info. and this is a kind of base 64 encoded string. So we can decode this to find out the exact secret information. What is the exact secret information, by using echo command and then our message, and then pipe it to base 64 hyphen d means decoded data. So the output is this, this is the secret message, which is like meet me at New York airport at 5 p.m. So this is the secret message. So the aim was to understand the tools which I have used in this particular case, in this particular challenge. So I have used basically file command, which was like used already in previous videos, and after that we have used LDD command. This LDD command is used to find the dependencies of the binary file, like what are the library files which is used by these binary files. So in this case we have found that there is one file which is not found by the system, by this particular binary. So we have resolved this issue by again finding finding our library file in the image file. So we have extracted our binary file, our library file, which is a binary kind of binary file, in this particular image file. So we have extracted, which like this binary file was this binary file was hidden inside this particular image file. So we have extracted the image file, sorry, we have extracted the binary file by using dd command, by using the dd command, this dd. Okay, so we have used dd, then we have used ldd, then we have used like file command, and at some point I have used readelf in order to clarify that that extracted data was like it was binary file or something else. So this was the basic challenge 2. So my aim was to give you a familiarity of these tools, how to use them in order to like extract bytes from any kind of file, and to test what kind of file it is. We use hex dump. So that's all for this video now. I will meet in the next part with another challenge in which we will use these tools plus another tools in order to solve the challenge, and we will learn something new in the next video. So till then, goodbye to all of you. So hello everyone, and welcome to the next part of binary analysis tutorial. So in this part I am going to show you how you can extract a binary file which is hidden inside another binary. I mean to say, there is a binary which has another binary hidden inside. So how we can extract that binary from the how we can extract hidden binary from a binary file, from binary in ELF file. So this is a scenario where I have like 3 binary. You can see we have 3 ELF files. One is hello world, the second one is hello human, and then third one is hello computer. So if we execute one by one all these, hello world, so it gives hello world dialog, and then if we execute hello human, hello human, then it will gives hello humans output. And then again if we run compute hello computer, then it will give hello computer as an output. So basically the situation is that here the situation is these two files is hidden inside this hello world. So in this case what we are going to do is we are going to take this hello world binary file and we will extract these two binary from this hello world. So like this is just I want to show you how these binary files reacts, like what are the outputs. And our focus is to extract these two files from this single binary file, because these two files are hidden inside this hello world file. So we will see how we can detect these binary files inside this hello world. Right now these two files are hidden inside this hello world, so we can't like if you run this file hello world, you can see this is just showing hello world. No, it's normal, it's not showing hello humans and hello computers, because these are hidden inside this binary file. So let's start to see how we can extract these two files from this hello world. So let's move on to our left terminal, and let's copy this hello world in the ch3 folder first. So cp and hello world, and inside one step back directory. So we are going to copy it in the ch3 files, and now we are going back in the ch3 directory. So we have hello world. Now we have this single file from which we are going to extract these two files. So first step is, how do we know that this hello world contains another binary file which is hidden inside this binary? So the first step is you have to search certain patterns in this particular hello world file. How we can do this? We know that every binary or every ELF file has a magic bytes called ELF characters, ASCII characters in them. So we have to search that ELF magic bytes first in order to be sure that this hello world has ELF binary hidden inside this. So we are going to do hex dump -c, then we have our binary hello world, and we are going to search by using grep command. What we are going to search? We are going to search ELF. So this ELF, we are going to search this ELF pattern inside this hello world hexadecimal dump. So let's see what we get. So you can see there are three ELF characters. There are three ELF ASCII characters which is inside this hello world. As we already know that these two files are hidden inside this. So this is ELF of these, like we don't know which ELF is for which file. So this is first ELF, this is the second ELF. So we are sure, like we have confirmed that somewhere in this hello world file these two files are hidden, and by definition we know by definition that every binary file start with this particular magic header bytes. Every binary starts with these four magic bytes. So these are the 4 magic bytes, and these are also the 4 magic bytes. So what we are going to do here is we are going to extract these bytes from this location. So first we are going to extract this one, this .elf. So how we can extract? We will use our dd command, but before using dd we have to first find the correct address. We have to find the correct address, correct location from where we are going to extract this particular elf, or like elf data byte. So let's count. This is 60, as you know, this is 60, then 61, 62, 63, 64, 65, 66 and 67. After 67 we have this 68. So from 3E68 our magic bytes starts. So our address would be 3E68. So we are going to use printf in order to find out the exact number of bytes from where we would start our extraction of elf binary. So here %d, and after that we have to mention our hexadecimal address. So in this case 3E, and this is 60, and we have, like, this is starting from 68. So in this case we have to put 68 here. So as you can see, this is the exact bytes, this is the exact location of bytes from where this elf is starting, this 4-byte elf. So now we have got the correct bytes from where we are going to extract the elf bytes. So we will use dd space and our, like, from where we want to extract the location. So we are going to use skip for that. Skip, then we have 15976 15976, and then we are going to specify the input file. In this case our input file is hello world, and our output file will be like f1. Let's see, we are giving f1 name, the extracted output, and then after, what we are going to do, we are going to specify the block size by using bs, which is block size, which is 1. So hit enter, and then we have extracted those bytes from here. So let's see, this is the f1 which we have extracted from this hello world. So first let's verify by using readelf utility. By using readelf we are going to confirm that this extracted file is a binary file by using -h to see the headers, to view the headers of this f1 file. So as you can see, all the bytes are in correct position. That is why it is showing all the information of this particular binary file f1. So it has all the, like, information like entry address and all the section header and program header information. So now what we can do, we can execute this further. We can see all these sections, all these things, like we can see read elf hyphen void and then -s for section, and then we can see all the sections of this particular binary. So we have extracted, like, in a correct way. That is why it is showing all the, like, information here of that binary. So now what we are going to do, if we try to execute this particular file, it is showing that this is like permission denied. Why? Because this file doesn't have execute permission. So let me give the execute permission to this file. Now it has execute permission, so now we can try to execute this file. So let's see. As you can see, the output is hello computer, hello computers. So now which file is this? This is the file hello computer. Now this we have extracted this hello computer file. So now let me rename this file to hello computers. Rename this file to hello computer. So we have extracted the hello computer, but you know, this hello computer, now this hello computer contains our hello human, because we have extracted. Let me show you by using hex dump -c, then hello computer, and then we are going to filter this ELF. As you can see, this hello computer is this hello computer contains two ELF headers, like two ELF magic bytes. The one is itself, like this ELF is his own, this ELF is its own header, like its own magic bytes, and this is another ELF magic byte, which indicates that this magic byte would be of this hello human. So there is no possibility that, like, it's not possible in general way that there is two ELF magic bytes in a single binary file. So what we are going to do is, we can extract this ELF, like these bytes, from this location and dump it. And after dumping, let's examine that file and let's see what that file will be. When we execute, we can find what kind of file that is. So let's do the same steps. So before doing some kind of like extraction, we have to find out the exact bytes, the location of bytes from where we are going to extract this particular data. So if you see here, this is 63E60. If you count from here, you can count like this: 60, then 1 2 3 4 5 6 7, 6 7, then 6 8 6 9, and then after 6 8 and 6 9, there will be 6A. Okay, so in hexadecimal there is no 10, like there is no count of 10. It will be A. 10 is represented by A. So here this 6 will be 6, and after 9 there will be like this, the counting is 6A. So if you count from here, it will be 3E6A. So we are going to put this particular location and extract these bytes from here, from this location. So we have to first print, like we have to know the exact bytes from where we are going to extract those bytes. So let me use printf and %d and new line. Then we have to specify the address, in this case 3E, then 6A, and this is the exact byte from where we have to extract from this particular binary hello computer. Now let's use dd, and we specify the location by using skip option. Skip is equal to 159 78, and then we have to specify the input file. In this case we have hello computer, and then if we specify the output file, in this case f2, we use f2, and now block size, which is 1, and then enter. Now it has extracted all the bytes, and all the bytes is in f2. So let me first verify by using readelf -h f2. As you can see, all the informations are correct. It's not giving any kind of error. It means that it's clean. It's a clean binary bytes. So we can execute this f2 by giving the execute command. Now if we execute this f2, you can see this is showing hello humans. As you can guess, this hello humans, this is the output. So we can rename this to hello humans now. Hello human. So now we have extracted hello computer from this hello world binary, and this hello human from this hello computer binary. So we have successfully extracted. We can extract this hello human from this hello world also, which is the same procedure, like which is the same technique which we have used from hello computer binary. So this is the simple way to extract a binary from a binary which is hidden inside a binary. So we can extract any kind of hidden binary which is further hidden inside a binary. Like binary is hidden inside a binary. In that case, we will use this kind of steps. So I think you have enjoyed this video, and I will meet in the next part. Till then, goodbye. Hello everyone, and welcome to the next part of binary analysis tutorial. So in previous part we have extracted these two files from this hello world, hello human and hello computer, but there is a problem. Now what kind of problem is there? If we see the original files, you can see the size of these files. These are the original size. Hello human has the size of 15960 bytes. Hello world has the size of 47916. Let us see the size of extracted binary files. If you see carefully, this hello computer has 15960 bytes, and as you can see here, this hello computer has 31940. So the size is difference, like there is a difference in the extracted size. Why? Because this hello computer also has this hello human bytes. That is why it is kind of double to its original size. So in hello human, if you see hello human, this also has 15960, but this hello human has 15962. There is a 2 byte difference. And in case of our hello world, which contains all these two binary files in them, this is like correct bytes. This hello world has correct bytes, because we didn't edit, like we didn't have, like we didn't do any kind of edit with this file. So So how uh, we can solve this issue, because these are the extra bytes, and in case of like uh, if you try to find the MD5 hash of these files, MD5 sum. So these are the MD5 hashes. If you check the MD5 sum of these files by putting MD5 sum command, you can see these hashes are also different. You can see this hello world has a different hash, and this this hello computer has different hash, and this hello computer has different hash. This also has the difference in the hash. This hello human has different hash, and this hello world has the exact same match of the hashes. So how we can correct this problem? How can we correct these problems? How we can find the exact bytes so that this would be the same exact copy of these original binary files? We can do this by one technique. It's kind of a formula by which you can extract the exact bytes of any particular ELF binary file. So let's see how we can do this. So for that, you have to first use read ELF. Read ELF, then you have to view the header. You have to view the executable header of that file, of that particular extracted file. So in this case, this is hello human. So let's see what this hello human has in its program header. So as you can see, these are the information which we have extracted from the hello world. So this hello human has the header of, like, these are the headers of executable header, you can say. So how we can count the exact byte of any kind of ELF file? We can do this by using a simple formula, which is let me show you by calculation in Python 3 shell. So I'm using Python 3 shell for like calculation purpose here. So you have to take section header. You have to take start of section header bytes, in which is this, in this case 13976, and you have to add this this number with the product of number of sections, in this case number of section headers into size of program headers, number of program headers, size of section headers. So you have to multiply size of section headers with number of section headers first. This is the first part. You have to multiply this section header with number of section headers. Like you have to multiply size into the number of section headers. You will take these two data, like you have to use these two information, which is a size of section header and number of section headers. First you have to multiply these two numbers, which is in this case 31 into 64. This 31 and this 64. First you have to multiply it, and you will get the output 1984. So now what you have to do, you have to add this number to the start of section header number, this is the start of section number header. You have to add this with this output. So in this case 13976, this is the exact number 13976, plus you have to add this with this output 1984, and this is the exact bytes. This is the total bytes. You can say this is the actual size of the hello human, which is this in this case. So actual size, as you can see, the size of bytes, this is the original hello human binary, which has the size 15960, and this is the output shows that this is 15960. So this is the way you can calculate the actual size of bytes, as actual byte size of any particular binary. So with this information we have calculated this these bytes from the section header, start of section header with section size of section header and number of section headers. So this is the formula which you have to use in order to calculate the actual size of bytes. So after that, what we have to do is we will use dd again, and we will specify the exact bytes. Like we will use this information in order to extract the exact number of bytes from our extracted data, extracted binary file, which is in this case hello human in this particular directory. So what we have to do is all the method is same except we are providing the exact bytes. So in this case, first we have to use skip. In this case, the skip is like we know the skip would be, in this case the skip would be like we know the exact, like we have already extracted this, so the skip would be 0. We are starting from the 0th like starting of the data bytes. So we will use 0 in this case from this like particular binary. So we will use 0 and space, and then after we will use count. So what is the size of the binary we want to extract? What is the actual count of bytes we want to extract from the location of 0 byte? So count will be our this number. Count will be this number which we have calculated. So this will be 15960, and in this case our input file is this hello human. Then output file we will give it a name like original hello human, and then we specify the block size, which is 1, and then enter. So now we have original hello human. Okay, so now we have original hello human, and now if we ls, like if we want to see the size, we use -l option of ls command, and now let's see the size of this original hello human binary. You can see the size is 15960, which is the same size of the original. Now if we do md5 sum, if we calculate the hash of md5 sum of this file, you can see this hello human has like this is the original hash, and in this case we have our original hello human And if you can notice, if you notice, this is the same hash as of our, like this looks same, exactly same from this. Like you can clearly see that these two values are equal, these two hashes are equal. You can see this is starting from 62178b, this is also 62178b, and this is ending with cef8. So we have extracted the exact amount of bytes of a binary in a correct way. So if we now, the only thing which is needed in this case is put the execute permission on this file. Now we have executable file, we can run it, which is like running successfully, and we can remove this hello human file, and now we have original hello human. So this original hello human is exactly the same as we wanted. This is exactly the same binary which we have left in this folder. So this is the correct way of extracting our ELF file from any kind of binary file. So through this video, like I have shown you what is how you can calculate the original size by using simple formula. So I hope you have learned something from this video, some interesting things. In the next part we will continue. Till then, goodbye. Hello everyone, and welcome to the next part of binary analysis tutorial. So in this part I'm going to show you how to use strings tool in order to find the hidden information inside a binary. So for that I have written a simple code for our practicals. So this is a kind of challenge, and let me show you what is the challenge. So this is our source code in which we are going to compile and create a binary file. So this is simple code in which I have declared a character variable in which I have saved a password like this. This is a password, this is a kind of string, like collection of characters you can say, and we have an input character data type which is of length 10. Then I have declared an integer result, and after that I am requesting from the user that input the password, please input the password, and I am taking the input into this particular variable input. And after that I am using string comparison. I am using string strcmp function which is checking these two inputs, which is checking the input with this value, with this value of pass variable. So actually it is checking our input with the stored password inside this program, and based on this checking it will show show us, the user, that it is correct or it's not correct. So it will show if the password is correct, that it will show correct, and if password is wrong, then it will shows us wrong password. So this is simple like program. So we will use string tool to find these hidden information inside this binary file. So how we can do that, let's see. So let me override this and let me uh, compile this with gcc challenge c output in we are going to give the um, name challenge. So we have this challenge file. Now if we run this file, let me first run this file. It is asking input the password, so I'm going to give some random value. So it is showing wrong password. So if we have strings tools in our system, strings is a tool which is installed by default in your Linux operating system. So if you use man strings, you can see the whole information about the strings. Print the sequence of printable characters in a file. So it will if you use this tool, what it does is this print the sequence of printable characters in file. All the printable characters will be printed if we use this tool against any kind of binary. So let me show you how you can do this. String space and then our input file, in this case our challenge file, challenge binary file. So we hit enter. So in the side terminal I am going to open the source of this file, source code of this file, so we can correlate the output. So this is the output of our string tool. So in the output you can see these are the sections. These are the sections. You can see these are the sections. Dot comment, dot bss section, dot text sections, dot init sections. And if you see here, these are the symbols. So these are the symbols. And after that, these are the strings. These are the characters, printable characters. These are the printable characters which are stored inside this binary file. And if you look carefully, you can see this is a secret character which is password in this case. This is the password which we have defined here in the pass variable. So this has revealed here, this particular string is revealed here, and you can see these are also shown here in the dump. Input the password, correct and wrong password, these are all printed here in the string output. And if you look carefully, it also printed strcmp, which is the name of the function which is checking our password, our input password, strcmp. And we have it gives the function name puts, which is used to print the messages of our program. So this is the output, this is the way of this is the working of strings utility. So you can use strings on any kind of binary file in order to extract the printable characters of that binary. So you can dump the you can dump the hidden characters inside the binary. So this is a simple example. By this example you can analyze any kind of binary, and you can see all the ASCII printable text characters. So that's all for now. I will meet you in the next part with a new topic. Till then, goodbye. Hello everyone and welcome to the next part of Linux binary analysis. So in this part I'm going to show you what is the use of strace utility, or you can say strace command line tool. So strace is a simple utility in Linux which uses to trace system calls of any kind of binary or ELF file. So in this part I will show you a simple demonstration by which we can we will see how we can trace a system call which are used in our ELF binary. So let's first create a simple binary first, then we will analyze that binary. So let's see, I have already written a simple assembly code for hello world. Let's see how it looks like. It's very simple code. As you can see, here we have written write system call. I have used why I am using assembly program, because there is a reason why I am using this assembly code, because specifically I want to demonstrate you that whatever we use in this particular file, whatever we call, like I have called this write syscall and this exit syscall. So we want to trace these system calls by the strace tool. So I have written this write system call in which I have printed message, and my message is hello world from, like, this is the message. So this message is passed, like this message is passed to our RSI register, and it will finally it will print by the write syscall, and then we will exit the program. So this is a very simple code in assembly. So let's compile it first. So for compiling we will use AS for assemble, and then we will specify our source file, which is hello.s in this case, and after that we have to specify the output. In this case our output will be hello.o. .o means we are assembling it, so this will be an object file. The output will be an object file. So we have our object file hello.o, and now we need to link this object file to create a binary. So let's link it by using ld space then hello.o, our object file, as an input, and then -o for output. So let me give hello as an output. So we have our hello binary file. If we can check it by using file command. As you can see, the output the output is ELF 64-bit executable. So we have our binary. So let's check it by running it hello. So it's the expected output, hello world from write system call syscall. So if we use strace, the syntax of using strace is simply strace space. And by the way, if you don't have strace in your system, you can install it by using sudo apt get, or you can say sudo apt install then strace. You can use this command in order to install your strace utility, but in my case I have already installed it, or maybe in your system it has already like pre-installed on your system. So let's use it by using by providing the strace command. So strace space, then we have to provide our binary file. In this case we have our hello, but you have to put this particular dot and / in order to run it also, like you have to run parallel with the strace. So let's hit enter, and after like hitting enter, You can see these are the list of system command, like system. These are the list of system commands, system commands, or you can just syscalls. These are the syscalls, system calls, which are used by our binary, which are used by our ELF binary file. So in this case, our binary file is using this particular. This is the first syscall. This is the second syscall, which is write, and this is the third syscall. So our strace has used basically 3 system calls in order to execute this hello program. So these are the 3 syscalls. The first one is execve. What is this? This is actually a system call which uses to execute this particular binary. It is used because without this we can't run this hello binary. So the first syscall always if you run any kind of binary on your terminal, this execv call will be the first syscall in order to run this binary. So it is needed to run any kind of binary file. So it will take, like this will take 3 arguments. You can see the first argument is this particular the file name, which it needs to be the file which needs to be executed is the first name of the file. So this is the name of the file which needs to be executed. This is the first argument. Now in the second argument, it takes the number of arguments for that particular binary. If we have provided some kind of argument after this hello, it will be printed here. So this particular argument holds the number of argument section, it is a kind of array of arguments which will be passed, which is passed to this binary. So in this case there are no arguments, only the first argument, which is itself the name of the binary. So by default it has shown us the 0 index argument, which is itself hello name of the file. And then we have environment variable. So this is kind of environment variable in the third part. This is not it's not very important here, but the important part is these two arguments. So in the first argument, the name of the binary file which needs to be executed, and in the second it has this is the number of argument. So this system call uses these information in order to execute our binary. So this is the first syscall, and the output of this syscall is 0, which means that this syscall has successfully executed. Now the next one is write syscall. We have used write syscall in our binary. As you know, we have used write syscall, and in write syscall we have passed this string, this ASCII string, which is hello word from write syscall, and this is the third argument, which is 31, and this argument tells us that this is the number of characters, this is the number of characters which is used in this particular string, in the message. So this is the number of bytes, which is 31, which we have passed in order to print our characters. So the output of this write is 31. The function output is 31, which is nothing but the number of characters we have used in order to print the to print our message. And after that we have only exit syscall, which is left. So we have used only 2 syscalls in our source file. As you can see, if we cat hello.s, you can see we have used only two syscalls. The first one is write, and then we have used exit syscall. But here if we execute our binary, it shows that it has used three syscalls. First one is execv, then second is write, and then third one is exit syscall. So it shows that if whatever you use in your program, like whatever syscall you use in your program specifically, it doesn't mean that the system will use only those syscalls in order to run your binary, because binary file needs different kinds of syscall when it executes by the system. So that is why it has used execve function in order to execute our binary. So this is a very simple case by which it shows only this particular extra syscall. But in general way, if you program in C and execute and test, then there will be number of different kind of syscalls, like system calls, which it uses in order to execute the program successfully, and I will show you. This is simple case, and let me show you some other part of some other options of strace. Let me clear the screen first. So if you want to know how many syscalls are used in this strace, how many syscalls, the number of syscalls used in your binary, if you want to know how many syscalls are used in your binary, then you can use -c command and then your binary, in this case hello. So -c option is used to count the number of times the syscalls are used. In this case we have used our binary has used write syscall system call, which is called only one time, and the next syscall is execve, which is used only one time. It doesn't mention the exit syscalls. This is the system's own choice. So totally we have used totally the hello hello binary used two syscalls, write and execv, and then actually it has used three syscalls, but it is showing only two. I think the default behavior, this is kind of default behavior of the output of strace. But by the way, these two syscalls are important for this binary in order to execute it. So this is a simple way to find out syscalls of any kind of binary. So let me show you another file. Let's create another file. Let's create a first let's create a new directory called syscalls. Then let's go into syscalls. Let's create a simple hello world program, hello.c, and let's create a very simple let's printf a simple message hello world, and then return 0. Let's compile it, hello.c, then output will be hello. Now we have hello executable. We can see this is an executable, 64-bit executable. Now what we can do is we will use strace command, strace utility, in order to find out how many syscalls are used in this particular binary. What we can do is strace space -c for count, and we will provide our hello file. Now at this point you will see there is a huge difference from the previous result. Let's see. As you can see, this is the output, and in this output you can see there is a huge amount of syscalls which is used in order to execute our binary file. As you can see, this is like read syscall used 1 times, a write syscall used 1 time, close. We are printing a simple message by this binary, but there is a huge amount of syscalls which is used. So you can see this is the write syscall which is used by the system in order to print our message, but it has read syscalls also, it has close syscalls also. Close has close syscall is used by 2 times. mmap memory mapping is used 8 times. mprotect memory protection is used 3 times. unmapping memory 1 times. brk 3 times. So these are like a bunch of different syscalls used in order to execute this binary. So strace is very helpful in finding the syscalls of any kind of binary. We can trace the syscalls like this way. If we try to trace any syscall in our binary, suppose we want to see how if there is a write syscall is used, if there is a write syscall used in our binary, then we can confirm by filtering it out, like -e. We use -e to filter out a particular syscall. In this case we are filtering out write syscall, and then hello. As you can see, it has filtered write syscall, and in write syscall you can see these are the arguments. So there are 3 arguments in write syscall. First is file descriptor, which is 1 in this case. The second one is our string, which needs to be printed, and it is passed in the second argument of this write syscall. Third argument is number of characters. So these 3 arguments is passed in the write syscall. Now we have other syscalls, like I'm not going to explain each and every syscall in this part, but let me show you the important ones. The important one is execve, which we have already seen in our previous program. So let me filter out this execve strace -e execve, and then hello. You can see execve is used in order to execute this program. So it has taken the name of the program as an first argument, and after that it has taken the number of argument as the second argument. The third one is environment variable in this case, and the output of this syscall is 0. Like this is a kind of return value, which is 0 in this case. In this 0 represents that it has successfully executed, like this syscall has been successfully executed. So in this way we can filter all the parts. But let me show you a very lengthy output, which I think is very complex to trace out. But you can try this. You can try to trace every syscall in this particular case. So simply just provide strace and then your program, and see. Now you can see this is a huge output. This is a huge output. Let me show you. As you can see from here, this is the output of system calls which are used. So the first syscall used was execve. This syscall is used because our program needs to be executed first in order to load it into the memory. So you can see this is the first syscall which is used, and after that we have I am focusing on the important one. This is the memory map. Now memory map is used for loading the program in the memory. It maps, it creates an area in the virtual memory space to load this particular program. So this is used here, mmap, and these are the arguments. Basically these are the like read write permissions. So the output of this particular function is an address. This is the address, memory address. And after that there are like this is called access, which is a kind of accessing the LD preload, or you can say this is system library which it tries to access. Then all the like other system calls executed one by one, you can say pread, mmap, then all these syscalls are used. And at the end you can see we have our write syscall, which is used in order to print our hello world message. So this way you can like trace all the system calls of a system of any kind of binary. So this is the this is the basic way of tracing the system call of any kind of binary file. So that's all for now. In the next part we will continue our journey of learning the new things in the binary analysis process. So till then, goodbye all of you. Hello everyone, and welcome to the next part of binary analysis tutorial. So in this part we are going to analyze the instructions of any binary in the output of object dump. So for this example we have a crack me, like we have a binary which needs to be cracked. So we are going to crack this binary. Now the crack means we have to solve this challenge, and while solving the challenge we will learn the actual analysis of instructions of our binary in the disassembled binary, like disassembled assembly code. So let's see how we can do this. First let me run this binary. Now this crack me binary is expecting some kind of secret string, so let's give something, and this is a wrong password. So we don't know what is the actual password, so we have to find out the actual password inside this crack me. How we can do this? First, because we don't have to use strings here, our focus is to use object dump and the disassembled code of this binary. The rule is we only have to use disassembled code, and with the disassembled code we have to find out the actual password. So let's use object dump. Let's dump the disassembly of crack me -d and crack me, and hit enter. Now we have the disassembly of our binary. So as you can see, this is the main function. This is the main function disassembled code. So as you can see, we have these instructions, push, move, and all this. So now how we can find our secret string of crack me? For that we just analyze the code. Now the first step is, in order to find out the secret string, is the first step is where this program is taking input. So as you can see here, this is the scanf function by which the program is taking our input. So this is the call to scanf. So at this point the program is taking our input, and after taking the input, the input is stored into somewhere. So if you see carefully here, you can see that this is our input string, 0x30 RBP. This is taking our input, and this input is transferred into RDX register, and after that this particular area is again copied into RAX. So actually this is just, this part is copied into RAX, and again this like this RDX is like our input is transferred into RSI, and this RAX is transferred into RDA. So now the actual part is the focus will be here, this RAX, because there is something which is transferred into RAX. So as you think, you might guess that if you look carefully, like we have to trace this part and this part. So if you see the RAX, you can see this RAX is here also. So we are not sure that whether this RAX is contains any kind of like secret string. But if you look carefully, this 0x50 and RBP, this register, RBP register, you have to trace, like first let me trace 0x50. So if you go up and here we can find 0x50. This is the register which is used here, 0x50 RBP. So this is exactly the register, like this is exactly the same register which are used here. So let's find out this, where this register came from, like where the values came from this register. Again, this is there is some move instruction from RAX. So RAX is transferred into this part, like RAX value is transferred into this RBP. So we have to again find out the RAX in this case, because our secret string is stored somewhere in RAX. So let's see where RAX came from, this RAX. So if you see carefully in like upward direction, this is RDX, not RAX, but after that, after the RDX, then here is RAX, which is exactly the same. This is also, so as you can see, if you look carefully, there is some value, there is some hexadecimal values which is transferred into this RAX. So what kind of hexadecimal value is this? This is transferred into RAX, then something is transferred, some other value, some other hex value is transferred into RDX. So this is kind of something suspicious, because this is in long length, and this is also suspicious because this is also a long hex string. So if we let's try to convert this hex into printable character. So for that we use echo, and then our string, our hex character. So in this case the first character would be 67. We will do this recursively, means we will do this like from the backward, due to the fact that this is little endian, this is in little endian order. So we will convert these hex values into their respective characters, or you can say ASCII codes. So first let me convert this 63, because this is also a hex string, and this looks also has hex string. So let's try for this 63. So let's see, 63, first 63, and the next will be 6b, 6b, the next this 6b, and the next. Let me copy the whole part so that we can do it at one step, at one shot. So in between we have to put our format delimiter. So after that we will use the next bytes, next hex bytes. Let me paste it, and again we are using the delimiter. It's a long string. It's very long string. Let me increase the size of the window. So that's all. I think that's all hex string. And let's print these hexadecimal characters. So as you can see, this is some kind of reversed, like it's a kind of reverse characters, some reverse character, which is kind of, if you look carefully, double P-Y, happy, then C-R-A-C-K-I-N-G, happy cracking. It looks like happy cracking. So I have like reversed all the hex bytes, but if you reverse the whole string, like this whole series of hexadecimal values, then you will get this you will get the output in the right way. So the 48 will be on the first, like if we have taken this 48 first, and then after this 61, then likewise if we have gone through 67, then we will get the clear, like in a correct form, like we will get the correct form of this string. But anyway, we have solved this challenge by analyzing these instructions. These are the instructions of the main disassembled code. So you can use this kind of this kind of approach of analysis. We have analyzed the logic of this particular binary, where we have spotted this scanf, and after that we have spotted this string comparison, and then from this from these instructions we have traced the actual secret string which is used in this program to identify, to verify. So let me show you. Let me execute the program again and provide the right and input the right password. So let's see, crack me, and we will put this happy cracking string. So HAPPY, happy cracking. So as you can see, this is the right password and access is granted. So through this method you can actually analyze the instructions of the main function. So in order to do this approach, you have the clear understanding of assembly language. You should know how the assembly works, like the basics of assembly. Without that, you will not be able to trace the actual code flow in the program. Like we have used this disassembled code of crack me. This is the disassembled code. As you can see, this is the main function disassembly. This is the main function disassembly, and these are the assembly, like these are the assembly codes. So you should know the basic syntax. You should have the common understanding of the basic assembly syntax, like what is this move, what is this sub, what is this XOR, what is this move ABS, and what is this part, like what is this whole instruction is telling us. What is the meaning of these things? You should know. So without the knowledge of assembly, you will not be able to understand any of this. So that's all for now. We have solved, we have analyzed the disassembled code of our binary. In this way, you can use this skill to analyze any kind of binary file. So I will meet you in the next part. Till then, goodbye. Hello everyone, and welcome to the next part of binary analysis tutorial. So in this part, I'm going to show you how you can analyze any binary while it is in running mode. It's called dynamic mode, analyzing in dynamic mode. So dynamic mode means when the binary is in running condition, is in execution condition, like is in executing state, then how we can dump the string information, like how we can dump these strings from the memory. So in this tutorial, I am going to show you how we can reveal this particular secret password in this program, how we can dump this particular password which is going to match with this string comparison function. So we will put a breakpoint somewhere inside here, like we will put somewhere here a breakpoint inside our debugging program, and we will see the value of these variables. Like we will trace out this part from here. So let's see how we can do this while program is in running state. So I'm not going to use, like our task is not to use strings at all, because that part is for static examination. In this part we are going in the dynamic part. So program should be running in dynamic part. That is our motive in this video. So I'm using a GDB tool in this part. GDB is a tool used for debugging the binary. So GDB-Q and our our binary. But let me first show you how this binary behaves, like how this binary looks like when we execute it. So let me execute this crack me, and we put some kind of secret string, and this will gives us some kind of message with wrong password and access denied. So the focus of this tutorial is to search this secret string inside the binary. So let's let's load this binary inside our GDB program. I'm using -q. -q is used for skipping the banner of the GDB tool. So if I don't use a -q, then it will simply just this is the banner. So I want this banner to be skipped. I don't want to show this banner by the GDB. So for that we have to use -q option and then our crack me. So now this crack me has been loaded into our GDB tool. Then the next step is we have to disassemble the main function. So this is the disassembly of our main function, as you can see. So here is the code. This is our actual source code, and this source code, this main function is converted into this disassembly. This is the disassembly of main function, as you can see, main. Now as you can see, there is like lot of instructions, lot of assembly instructions are there. So now the first task should be like we have to trace, like we have to see all the function calls. Now the first function call is printf, which indicates this printf function in which this message has been printed. After this printf we have scanf function, which is here, this scanf. So this scanf is here, which is called at this particular memory location. And after scanf we have another function which is string comparison, strcmp function, which is called here. So this is the function in the if statement. And after string comparison we have like puts, which is this part, wrong password. And after that we have again a put which indicates this particular printf statement. So after that we have like exit syscall, in which the main function just exits. Now we have traced all the functions, this printf, this scanf, string comparison. Now our focus should be first on the input. Now this is the function which takes our input. So actually after the input, our input is compared with something. So after getting the input, the program is taking our input and giving this input to string compare function. So this secret password should be between these two functions. So this password is somewhere hidden inside this part. Now this is one way, like this is the direct approach by which we can unhide this secret message, this secret password in this case. There is another way also. That way is like you have to trace back, like you have to trace these data upwards. You have to trace back these registers upward direction, in the upward direction from where it came. So if you trace these like registers upward, in the upward direction in the program disassembly, you will find out that these registers data is initialized here. As you can see, I am like I'm sure that this is the actual string, the secret string, which is initialized here. But for now I am leaving it to you as a homework, as a task, that you will find out. You have to find out this black hats part, this black hat string somewhere here. Okay, from this register, from these registers. You have to trace back. So for now we are focusing on these parts. So we are going to investigate or analyze between scanf and string comparison function. So we have to put a breakpoint in order to analyze these like these registers. We have to put a breakpoint somewhere here before the string comparison call. So before putting a breakpoint, let's decode these instructions first. So the first instruction is load effective address. So it is loading address of this register into RDX. So this register contains some like some data. What kind of data this register is? Like RBP, then 0x70. This is like a relative address of RBP. So this holds a data which is transferred into RDX, and again this RBP also holds a data which is again transferred to the RAX register, and then again these two registers is transferring these data inside another registers which is RSI and RDI. So why they are transferring this data to RSI and RDI? If you know, there is a system call, like there is a function call, not system call. This is a function call strcmp, and this strcmp string comparison function needs two arguments. The one is our one is the password which is saved inside this, the secret password which is saved inside the program, and the other argument is the other parameter is input which we have passed. So these two registers contains these two values. One register contains the password or maybe the input, and the other contains password or input. Means these two registers contains the one of these informations, one of these piece of information. So we have to inspect these registers before it goes to strcmp function. That is why we have to put a breakpoint somewhere here. So, from here to, like, we can use this address also at this point. So we will investigate these two registers, basically RDX, RAX, and we can investigate these two also. In case if we didn't found anything here, then we will investigate these two registers. So in one of these registers we should get this secret information and the input on the other in other register. So let's put a breakpoint first by using b b command, and b space then asterisk symbol. Then we have to copy and paste the address. So the breakpoint has been set, and let's run the program. Now there is a problem, cannot access memory at address. So we have to try to put another breakpoint. Let me first delete this breakpoint. Delete breakpoints. Yes. Now we have to put some, we have to put a breakpoint on some other address. Let me put here a breakpoint. Cannot access memory address at this location. Now we have only one option. Let's try to do this. Let's try to delete first. This is a very common problem which comes very often. Cannot access. Now we have to exit from the GDB, and again we have to load the program. Track me, disassemble main. Now we are going to put a breakpoint again, run the program. Again it's not, cannot access the memory address. Okay, so let me delete again all the breakpoints. It's a kind of annoying part. Let's try to put a breakpoint here again. Copy and put a breakpoint here. Let's try to run. Okay, continue. Command aborted. So guys, due to some reasons, there are some technical problems which I was facing in GDB while putting some breakpoints. So I have resolved the issues. Now we can continue our practicals on this part. So let me load the crack me again in the GDB, and let's disassemble the main function. As you can see, this is our main function. So we were at here, like we were at this location where we were going to put a breakpoint at this location so that we can get the strings of, like, we can get the data which is stored in RDX and RAX, so that we can find out our secret string as well as our input from this location. So what we are going to do is, first we have to put a breakpoint at this particular call, strcmp. So let me copy this location and put and paste it here and put a breakpoint. So now the breakpoint has been placed at this part, at this location. Now we can run it. Now it is asking us, like it is asking for the password, secret string. So in this way, like in this situation, I am giving a capital X many times. Now it has hit the breakpoint here. Now program is paused at this location. So now at this time we can see the value which is stored in this RDX register. How can we see that? Using x//s command of in the GDB. X means examine. We are examining. I'm not able to pronunciate that. Examination, you can say. We are examining some data, and I am giving S option. S means I am dumping out the strings. Whatever is inside these registers, we are going to dump it as a string format. So we are going to provide the string RDX in this case. So this is the RDX, and we have now we will check what this RDX is. So let's enter it. As you can see, this is our input. So what I have what I have inputted here is reflected in the RDX register. So now the next register is RAX. So this RAX, what does this RAX contains? Let me see. RAX, as you can see, this is the secret
message. This is the secret message, secret string you can say. Black hats is in this particular register RAX. So this secret string is transferred from this part, and this part is located above, like in the you can say upward direction somewhere, like from the start of the program, from the initialization where it was initialized somewhere inside this part. So you can trace out that, but for now we have uh, found our secret string inside these registers. So now we revealed these secrets, like secret strings inside these registers. How can, like how we did this? We did this because we have some kind of basic knowledge of assembly syntax. We know what is going from here and there. We know the syntax, what this does, but like what this lea means, what this call means, and what are these function indicates, like what are these names indicate here. So you should know the basics of assembly before going into this. So I hope you have got my point, what I wanted to teach you. So in this way we can like we can find, or we can analyze the binary inside the GDB while it is running. Now this is in the running state. I have paused the program. We can continue the program by using C command. So as you can see, wrong password, access denied. So if we run the program again, if we give black hats, now it again hits the breakpoint, and now we can again see the RDX register. In the RDX register it is black hats, and what is inside this RAX register, let me see. This RAX register also contains black hats. So in this case the both variables are the same, the contents of both variables are same. So when the both variables are the same, input and pass, then it would, like it will print the right password dialog. As you can see, the output is right password, access granted. So this is the correct way to analyze the execution of like binary. You can find out different kinds of strings from where, like where it is initialized, like the location where it is initialized, the location where all the functions are used. Like you can trace every part. Like this is the basic these are the basic steps of analyzing a binary in GDB. So I hope you have learned something from this video. I will meet in the next part. Till then, goodbye.
Hello everyone, and welcome to the next part of Linux binary analysis tutorial. In this part I'm going to show you how you can use GDB in order to view the disassembly in the dynamic state of any binary. In this case we have my bin. This is the binary which I am going to show you how you can use GDB in order to dump all the instructions which are used in this binary while it is running. So let's see how we can do this. So let me first show you the information of my bin file. This is 64-bit LSB executable, and now the next part is we are going to use GDB. So let me switch my terminal to something which you can see clearly. So now what I am going to show you, GDB -q and my bin. file. This is my file. Now now the first step is you have to find the entry point of our binary. So let me first use info file. So by using info file you can find the entry point of this binary, which is this in this case. Generally what we have used till now, we have used like this disassemble main. So we have used like this assemble main command to disassemble our main function, but this is not the correct way. If you want to disassemble the whole execution of any binary, you have to use this approach. Like you have to use these steps. The first step is info file, so that you can get all the you can get the entry point of this binary file, and along with these sections, like list of sections, you can see this is the text section, and the address of this section is 40105, which is same as the entry point. So let's go further. So let me clear the screen and use the command again. Info file, we have this entry point. We use this entry point to put a breakpoint there, so we can trace all the instructions from start to finish. So let me put a breakpoint, and let's copy and paste. So we have set the breakpoint at this location. Now what we are going to do is we are going to set pagination off first. Set pagination off, and the next step is we are going to set logging on. We have set the logging mode on, so we can log all the instructions to a separate file, so separate log file, so that we can analyze later. Now the next step is we are going to we are going to display all the instructions, or means all these all these steps, like all the single step instructions. We are going to display single steps one by one. So we use this display command, and after that we have mentioned I, means this will be only one step at a time, and then we have to use program counter variable. So in this case there are no, I have to switch. I think there is a color problem, so let me use green profile. Okay, now it's better. Now it's looking better. So in this case, as you can see, we have our program is not running. That is why it is showing the result like no registers error. So what we are going to do is we are going to run our program first. So run, and it hits the first breakpoint, in this case the start of our and this is the entry point. So it has shown us the first instruction used by this program in order to execute. So now what we are going to do is we are going to use while loop, while, and step into the second, we are stepping into every function. Like step into means use single steps to execute the binary one by one, like to execute every instructions line by line. When any function when you encounter any function, you will go into that function and perform all the instruction till the return of the function. So in this case we are going to execute every and each step in order to run this binary till the end of the till the exit exit of this binary. So step into and then end. As you can see, all the instructions are executed one by one till the end of the binary, end of this binary. So we can use Q for exiting this GDB. And now if you see, we have a gdb.txt log file is generated. So if we want to count the number of lines in the gdb.txt, you can use wc command. As you can see, there is 52,827 lines written in this particular file, in this particular log. If we see, if we want to if we want to see the lines, like what is written inside this gdb.txt, we can use less command. You can see these are the information which we have used while we were disassembling or we were debugging the binary. So as you can see, this is the first command we have used. Like we have used this command in the GDB to display the single instruction at a time, and you can see all these instructions are executed one by one, and we told the GDB that you should show us every single instruction one by one while it is running, while the binary is running inside this GDB. So you can see these are the instructions one by one. These are the instructions. So what we are going to do is, we have calculated the number of lines used in this gdb.txt. It means if we filter out only the instructions in this file, only the assembly instructions, disassembled assembly instructions in this file, we can count the number of instructions of this binary in order to execute from start to finish. We can calculate how many instructions are there needed in order to successfully execute this binary. How we can do this? We can use grep command. We can filter out with grep. Now what we are going to filter first, let's try to filter this particular symbol. So let's see what it gives. Now it is giving all the instructions. It is giving all the instructions which are, I think, let me less it. So this is the starting point. As we have seen, this was the entry point. Let me show you, like, side by side. Now we have this terminal, and now what we are going to do is, we are going to use a read elf utility to show the entry point. You can see the address, like the entry point address is 40105. As you can see, this is the same 401050. So this is the starting address, and from this address the execution has started. You can see, and it started, and it goes all, like, it has executed all the instructions till the end of our till the end of execution of this binary. So if we dump this, if we dump all this filter data into a new file called we can name this like actual disassembled instructions dot text, actual disassembled dot text. So now we can see the actual instructions which are executed by this binary one by one. You can see these are the list. If we minimize a little, you can see all these instructions are listed one by one. So in this way we have dumped the dynamic disassembly of our binary. If you compare now, if we compare the number of lines, means number of instructions of this binary which is needed in order to execute successfully this binary, what we can do is word count -l and then this particular text file. You can see 17,192 lines of code is required in order to run this binary. So these are the actual instructions. These are the actual instructions which are required in order to run this binary successfully from start to finish. If you compare this line with the static disassembled code with like object dump, we can use object dump -d and what is the binary, my bin, and we just dump the output into a file called static dump.txt, and let me show you less static dump. So this is the dump. As you can see, this is the static disassembly of this binary file. What we can do is like we can count the number of lines, means number of instructions of this static dump. So as you can see, the number of lines are 132. So we can guess like, let me remove 30 lines of let me remove 30 lines from this particular number of lines. Almost it will be like 100 lines of code. So you can see in static dump we have only 100, nearly about 100 lines of code, and in actual, like in the dynamic state, when the binary is in a running condition, when the binary needs to run, it uses 17,000 lines of instructions, as compared to static part. The dynamic part is much bigger, many times bigger from the static part. So you can see all the if you want to analyze, if we want to do analysis, in-depth analysis of any kind of binary file, we use both methods. First we use static method in order to find how the binary works, the basic binary working, and in dynamic analysis we use we find out huge number of instructions, there are thousands, 17,000 lines of code. So the analysis time is different in both sides. In static part we have our time consumption is very less in order to examine the static part, but in dynamic there will be a huge number of time in order to do analysis of this binary, because we have to trace these number of instructions in order to in order to know how this binary actually works in the memory. So that's all for now. This was the like the purpose of this video was to give you a simple uh, comparison between static and dynamic analysis. So this was the static dump and this was the dynamic dump. So now you have the basic idea of how what is the basic difference between static and dynamic dumping, like static disassembly and dynamic disassembly. So that is why dynamic disassembly is more important from the static disassembly. So that's all for now. I will see you in the next part. Till then, goodbye.
Hello everyone and welcome to the next part of binary analysis tutorial. So in this part I'm going to show you how you can modify the code execution with the help of simple tools. In this case I am going to use only two tools, two binary analysis tools, which is hex edit and object dump. I will use these two tools in order to change or modify the ELF execution flow. So let's see. Let me first show you the source code which I am going to use in this case. So let me nano and sample.c. So this is the source code in which I have declared a function which is ABC, and this function is just printing simple string which is hello from ABC function. And in main function we have a simple printf statement which prints hello world from main function. As you can see, in main function we have never called ABC function. So I will show you how we can modify the code, like how we can inject some code into the binary statically, not dynamically but statically, that will reflect the that will change the execution of this binary. So our task is to execute our task is to edit in such a way statically. We have to edit, or you can say we have to patch in a way that this program executes this part, like this program executes this ABC function instead of this printf function. So let's start. This is very exciting part. So I already have compiled this file into C1. The name of the file is C1. So let me execute this C1. You can see the output is hello world from main function. So now the first part is the most important part here is you should have a common understanding of how a binary execution works. So for that we know that when a binary executes, it uses start function first. It executes start function first by default. So how we can analyze that? We can use object dump in this case, object dump -d, and our binary in this case C1. So you can see this is our main function, this is our main disassembly of main function, and you can see this is putting this is printing some strings here, and you can see this is our ABC function, and this is the body of our ABC function. And if you scroll up, we can see this this is the start function. So this is the this is the default function which executes first, and this is the entry point. If you use readelf to know the entry point, you can see the entry point is 8049060, which is same 8049060, which is nothing but the start function. So this start is executed first. So after start executes, the first part is like what start does is this this is actually calling main function. As you can see from here, this calls the main function at this particular point. You can see here call and then this particular address. You can if we check carefully, this address is nothing but the address of main function. You can see 9040. This 9040 is not here, I think. Not this. This is actually libc function. I forgot to tell you. Now here it is. This is the main function, because the address of main function is transferred into EAX, so that this EAX is passed to this libc library call, so that it will call the main function and execute it. So at this point, when it moves the address of main function, which is in this case 91A1, you can see this these last 4 digits, we can check it, 91A1. So at this place you can see 91A1, this is the address of main. So for our task is to call the ABC function. You can remember by looking at the source code. Our aim here is to call the ABC function instead of main function. So what we have to do is we have to simply change this particular opcode into the ABC function address. So in this case, we have to focus on this area. We have to focus on this area. We have to change the machine instructions here, which is in hexabyte form. So how we can do that? We can do that easily with the help of hex dump and hex edit. So let's focus on the ABC address. But before going into ABC address, we have to first trace the actual location where it is transferring this particular address into EAX. We have to trace out this particular bytes in our binary so that we can change at that particular location. So we are going to use hex dump in this case, and if you see carefully, you can you can see here this A1, this whole address is transferred into EAX, but the opcode of this particular instruction is is written here, so in hexadecimal. So as you can see, this 8049 from the last one, A1, this A1 is nothing but this A1, then 91, then this is 91, then 04, then this is 04, and then last is 08. 0 is not written here because it is on left side. So this is 08. So we have to trace this particular address in our hex dump so that we can replace these bytes into ABC function bytes. So let me load it in, like let me hex dump of this binary and then filter the grep, like we are going to filter with this particular byte, like we are searching this byte on in the dump of this binary. So we are going to use C7, which is this byte. So we are locating 67. As you can see, it is located here, C7 C0. If you trace carefully, C7 C0, then A1, then A1, then all these bytes. So it is at this, like these bytes are located on these addresses, on this address, particular address 1080. So what we are going to do is, now the next part is we have to know the ABC address. This is the ABC address. So what we are going to do is we are going to use hex edit, and we will use color. In this case we are going to load C1, then hit enter. Now we have to go into that location. That location was 1080, so we have to scroll through 1080 address. So you can see here 79 1080. As you can see here, this is 1080. So this 1080, you can see this C7 C0 A1 91, all these bytes. So what we have to do is we need to change these bytes. So let's see how the order of the bytes, how the order of bytes are written here. So first it is C7 C0, then after C0 we have the address of our function, our main function. So in this case we are going to change these 4 bytes, I think, yes, these 4 bytes into our ABC function address. So let's do that. So let's see our ABC function, ABC function address. In this case this is 76. So we have to change from end to, like we have to change from left, sorry, not left, but we have to change the address bytes from right to left, from right to left direction. So the first byte would be 76. As you can see, you can compare it from here. This is A1, so the A1 is in first place. So we have to place 76 first. So 76 7 6, and then 91 is already written, and after 91 we have 04. So you can say 04 is already there, and then 08. So everything is fine. So I think there is there is 1 byte which is needed to change here. So let me overwrite this. Yes, file name is C1, and then exit. And now let's open the source code here, sample.c. So our target function should be executed now, because we have changed this main function address into ABC function. So ABC function will be called by start function in order to execute. So let's execute C1. As you can see, hello from ABC function. This function is called from that location. So our task is completed. If you again check the object dump output of C1, disassemble C1, you can see clearly that we have successfully changed the execution flow of this program by changing a single byte. We have changed only a single byte, this 76. We have changed this 76. Rest bytes are the same from the main. So we have changed single byte which has altered whatever you can say, which has changed the execution flow of this program. So it has executed the function, means it has executed the another function successfully without any error. So this is the this is a way this is a simple part, this is a simple concept by which you can put any function address here to execute that function at first. So you can experiment with this kind of method of any kind of binary. Just create a simple binary files and test like this, changing the addresses and testing that it is executing or not. So this is a kind of like security issues in binary, but here our purpose is not to learn the security part, but to learn the analysis of binary files. So that's all for now. I will meet you in the next part. Till then, goodbye. Hello everyone, and welcome to the next part of binary analysis tutorial. So in this part I'm going to show you how a code injection work, and after that we will see the practicals of code injection technique in binary. So let me show you the concept behind the code injection in the ELF file. So let's start. So as you can see, this is our format. You already know about this format. The whole binary is divided into 4 sections called executable, header, program header, sections, and section headers. So in order to inject any kind of code, what we are going to do is, first we need to find this particular section, which is .note.abi.tag. This is a section which is not much useful for the program. If we edit this part of the section, there is no impact on the program execution. So first we will try to override this particular section. Now the first step is we overwrite our code, which is in this case the virus code. I just named it virus because I want to do I want to create I want just in case I have written virus here. It's not a virus actually. It's a code. So this virus code is written this virus code is overwriting the bytes of this particular section, because this section is not very useful for the binary. That is why we have targeted this particular section. So we are overwriting this section with the bytes of our own code, our virus code in this case. So this code is overwritten here at this section. So this section is getting modified by the virus code bytes. So this is the first step. So the first step we are overwriting .note AVI tag section bytes with our virus code bytes. Now in the second part, we are going to overwrite .node section header with .virus with proper memory address and permissions. So we in the second stage, we have to override the section header table information. In that section header, there is a .node section like this .node.avi.tag section, and we are overwriting this section with our .virus code with proper memory addresses and permissions. This is the second stage. And in the third stage, we should have to change the program header section. Like we should change this part also in order to run our virus code successfully. So in the third phase, we will overwrite the pt underscore node section. So we are overwriting this pt node section with a code segment, with a code with a code segment of our virus code. So in the third phase, we are overwriting this pt node section of program header. So these are the three steps, and in the last final stage, we are going to change the entry point of this executable header with our virus code entry point, which is in this case this part. So this .virus section contains our entry point, and this entry point, we are going to take this entry point and put this entry point here in this particular executable header. And after that, all the process will be completed, and if we run this particular binary, our virus code should run first. After that, this binary will be will run. So this is the basic steps. Like these are the internal concept. We will use a tool called ELF inject. All these steps will be done by that tool, ELF inject. So let's see how we can do this. So let me minimize this. So as you can see, we have ELF inject tool we will use in this part, and we have hello file and we have virus.s file. So in this case, we have this virus.s file. As you can see, this is simply 64-bit assembly. This is the assembly, and this is a simple hello virus code. This assembly will print hello virus in our terminal. And for printing hello virus or any kind of printing, we know that we will use we use write syscall. So this is write syscall, and before write syscall, we are pushing all the registers into the memory, and after calling the syscall, we are popping out every registers from the memory, and then finally we are pushing, or we can say we are calling this particular address, and this address is nothing but, if we see the entry point of our hello in which we are going to inject our code, you can see the entry point is 401050. This is the entry point, and this entry point is same as this, because after running this part, after if we will inject this whole code into this binary, this hello binary. So when binary will run, then it will execute these parts. So after executing these parts, the program will return to its original entry point, so that it can run its own code, which is hello world in this case. So this is a way we are going to do, we are going to inject our code in this. So let's close this file for now and compile it. So for compilation we are going to use an NASM tool, and we will specify the format of this file, which is bin, and we are going to mention our source file, and we have to mention our output file. So in this case we have our output file called virus. So let's inject this virus with our let's inject this virus into this hello binary file. So we will use elf inject tool, and if we enter if we want to see the help, it will shows us that we have to mention elf, and after that we have to mention the inject means the file which we are going to inject. So the second argument will be our you can say payload, or this particular virus file. So after that what will be the name of the section, what will be the name of the section which we want to inject into section header table, and after that we should mention the base address, and after that we should mention the entry point entry. So in this case we will use -1 because we don't know we are not mentioning the entry point here. So -1 will be used. It is saying that if you are not using any kind of entry, you can use -1 if none. So we are going to use -1 in this case. So let me use this tool, elf inject space. So in this case our elf is hello, and after that we are going to inject this virus file. So in this case virus space, and then we should mention the section name. So if we look at sections of this particular binary, let me show you. Sections also is in this case, here is the sections. These are the sections of this particular binary. So these are the sections, and we are interested in this section. So we are going to override this section .note .abi .note ABI tag with our .virus section name. So we will use like this .virus. So this will overwrite this section with our mentioned our input here. So this .virus will be injected or override this part in this case. So this .note ABI will be replaced by this .virus. So space, and the base address. So in this case base address would be like 8 and 5 times 0 space, and then we are not mentioning any kind of entry point, so we will use -n as -1 and hit enter. So now it has like overwritten, it doesn't shows any kind of error. It means that this has overwritten, this particular section is overwritten with our virus binary file. So let's check it again and compare the results. So read elf hyphen wide, and in this case sections, and then hello. So let's see, and you can see that this section has been overwritten by this .virus section. So we have successfully overwritten this part, and there is one more part which I want to show you, which is in this case read elf hyphen l means header, program header. So if you see the program header of hello, you will notice that we have overwritten the note area, note type of program header with the load program header, with the type load program header. So this load resembles this this load resembles this particular virus section header, virus section. So this dot virus section resembles this load area, like this load part. So as you can see, this load has read and executable permissions, so that our own code, our own virus code can be executed in this case. So these are the two changes which the tool has done it for us. Now the rest is, now the remaining part will be to change the entry point, to change the entry point of this hello to our virus entry point, to our virus code entry point. If we run this binary, you can see this is hello world line. Now this is executing its own code normally. Now it is running normally. It contains our dot virus code. It contains our dot virus code, but in this case we have not edited its entry point. So let me edit this for you. So how can we edit that? We can edit by using hex dump hyphen color hyphen hello. So in this case we are editing hello. Not hex dump, hex edit, sorry for that, hex edit. So in this case, if you see, the entry point is, in this case you know already that every program entry point is the .text section address. So this .text section address is 4010.050. This is the entry point. This is the original entry point of this hello binary, which you can see here. 40, 10 and 50. This is the entry point. These are the bytes which shows the entry point of this binary. So we have to change this part into our virus entry point. So in this case our virus has this kind of entry point. So let's change this with our virus entry point. So now the first byte is 40. In this case this 40 should be changed to 0C. So let's change this with 0C, and the next byte will be 3E. Now 3E. Now the next byte will be 08. So in this case 08. So we have successfully overwritten the entry point, original entry point, with our own virus code entry point. So let's overwrite this with the file name, and then we can check it. Now we can check the entry point of this program. So as you can see, the entry point has changed to our virus code, to our virus file. So this virus has this address which is same as the entry point. So if we try to run this, let's see. Let's try to run this. Let's see if we have successfully injected our virus code into this. So as you can see, if we run it, we have successfully injected our code. In this case, this is hello virus. So hello virus has been executed inside this hello world binary file. So this is all these are the all the steps which we have covered, like this code injection. In the first step, the tool has overwritten the in one of these node.abi.tag section with our own binary code, and after that we have overwritten the section header. Then after we have overwritten the program header, and after that in the last phase we have changed the entry point of this executable header with our own virus code entry point. So that's all for now. This is the basic this was the basic concept behind code injection in binary. I hope you have got all the you have got all the idea in which these tools work, these injecting tools like code injection tools work. So thanks for watching, and I will meet you in the next part. Till then, goodbye.